Okay. This place. Okay. This place. This place. Hmm? Is it clear? Ah, you don't see clear. What's the problem like this? Or is this from your end? Is it this clear here? I don't know if this is clear from their end now. Okay. It says my okay. I see the comments here that yes, it is clear from someone's end. Okay. I'm expecting more comments. Please just send your message. I'll just review them to be sure that everything is alright. Is it clear from this side? Is it clear from your end? Zoom it. Hmm? Ah, is this manageable? Okay. Let's just continue with this then. So what I tried to explain earlier. So what I tried explaining earlier was that when you are taking a function as a function of another, for example, given f of x is equal to 2x minus 3 and g of x is equal to x squared plus 2x minus 7. So to calculate f of g of x, we already have f of x as 2x minus 3. So when you want to calculate f of g of x, it means you are taking the x here as g of x. So when you are taking x as g of x here, then the x here also you'll be taking it as the output of g of x. X here will be substituted with u with x squared plus 2x minus 7, and x here will be substituted with g of x. Now that's the same thing I did here. F of g of x is now equal to, this is 2x minus 3, but now we'll be writing 2x squared plus 2x minus 7 minus 3. So another example, given f of x is equal to e raised to the power of tan x cubed, then g of x is equal to tan, okay, and also g of x is equal to tan cos inverse of x. Then f of g of x is equal to f of g of x. X here will be represented with g of x. Then e raised to the power of tan g of x cubed, and g of x is given as tan cos inverse of x, then e raised to power tan g of x, then the cube. The cube will be written there. So that's why we have f of g of x as e raised to power of tan cos inverse of x, then everything cube. So I also gave one here. Okay, g of x is equal to square root of x. G of x is equal to square root of x. F of x is equal to x squared, and h of x is equal to e raised to the power of x. So to calculate f of g of h of x, you have to start from the back. This is h of x. So when you take the input of h of x, the input of g of x and h of x, so g of h of x will be started from the back. G of h of x is equal to, this is g of x. So you'll be substituting h of x for x here and here. So g of h of x will be equal to square root of, then x here will be represented with h of x, which is e raised by x. Then g of h of x, is equal to square root of e raised to the power of x, which is equal to e raised to the power of x over 2. Okay, g of h of x is now equal to e raised to x over 2. I explained before, I said the rule of indices that square root of x is equal to x raised to the power of 1 over 2. So with that idea, you you discover that square root of e raised to power x is equal to e raised to power x over 2. F of x is equal to x squared. Now, we've calculated g of h of x, but our aim is to calculate g of f of g of h of x. But our f of x is given to be x squared. So, function of g of h of x, g of h of x, which is already given, which we already discovered to be e raised to x squared. So, function of g of h of x will now be calculated by taking x here as our result for this, which is e raised to x over 2. So e raised to the power of x over 2 square is the demanded, and this is equal to when 2 cancels 2. So we have e raised to the power of x. So f of g of x, f of g of h of x is equal to e raised to x. An objective question may even suggest that which of the following is equal to g of f of g of h of x, given that f of x, okay, let's listen now. Given that f of x is equal to x squared, g of x is equal to square root of x, and h of x is equal to e raised to the power of x, an objective question the question may come in this form: that which of the following is equal to f of g of h of x? Then you'll be given the option: number 1, f of x; number 2, g of x; number 3, option 3, h of x. So, you might not know what to do, but in this case, we already have what you need to do first is to calculate f of g of h of x to be sure of the output. Now we have the output to be equal to e raised to the power of x. It means that f of g of h of x is only equal to h of x, because in this case we have e raised to x as h of x. So, and we see that our output here is also equal to e raised to x. So the right option would be h of x in this case. Another case, given that f of x is equal to tan x, g of x is equal to cos x, and h of x is equal to tan x, calculate g of h of x first. If you want to do anything, like you want to calculate g of x, you are told to calculate f of g of h of x. The first thing to do is to calculate h of x, and to calculate g of h of x. Okay, let me come again on the new page. If f of x is given as tan x, g of x is given as cos x, and h of x is equal to tan x again. So we want to calculate f of g of h of x. The method remains the same. The method is that we start from the last part of the expression, and the last part here is g of h of x. Now g of x is given as cos x. Now we want to calculate g of h of x, and h of x is also given as tan x. So g of h of x, as discussed earlier, is equal to cos. Now we'll be taking x as, we'll be substituting x with tan x. So it's equal to cos tan x. That is g of h of x. Now to calculate f of g of h of x, g of h of x is already given as cos tan x. Now f of g of h of x is now equal to tan of the answer. Instead of writing x, we now substitute x with this tan cos tan x. So that's just our answer. Okay, what if we are told to calculate g of f of h of x? G of f of h of x is the same thing as starting from the last two. So f of h of x first, and this is equal to tan, this is f of x, and this is h of x. So when you are taking f of h of x, that will be tan x, tan, and our x will be represented with this value of this output of h of x, which is tan x. So that is f of h of x. Now, if you want to calculate g of f of h of x, our g is equal to cos x. So g of f of h of x is equal to, our g is equal to cos x. So cos of answer, which is tan, tan x. Another question may suggest that another question may suggest that which of the following is not which of the following is equal or which of the following is not equal. Or let me just ask you that is g of f of h of x equal to f of g of h of x? Now the answer here is that it depends on the question you are working with. In some cases, it is possible that g of f of h of x is equal to f of g of h of x. It depends on the question, depends on the formation of the question. But in this one, we say that f of x, f of g of h of x is equal to cos tan tan cos tan x, and that's not equal to g of f of h of x, which is equal to cos tan x. So you need to observe all these things. Even there are some things about this course that with the little information you have, you should be able to expand it to get some other information that you do not have. For example, we know that if f of x is given as something, g of x is given as something. So if we want to calculate f of g of x, okay, let's say f of x is equal to x squared and g of x is equal to, let's say, x. Then you want to calculate f of g of x. So f of g of x is the same thing as putting the value of x into x squared, and we have our answer as x squared. So that's the information. That's the little information you have. Now you want to elaborate the information to get something like f of x is equal to e raised power tan cos everything. G of x is equal to cos tan something. And that one also is very long, like that number one question I was given in the test. So the method remains the same. You just need to be logical in combining the method, in combining the steps. Like what you know that if you want to calculate f of g of x, no matter how long the expression is, what you just need to do is to substitute the value of g of x into x for x in f of x. So that's the same method we do. No matter how long it is, just ensure that the steps are correct. You understand what you are doing? Hmm? Please, if there's no problem with it, please, I want to see your comments. Please comment your observations so far, whether it is clear or maybe it is not clear. I'm trying to gather some other questions. Actually, we do not really need to spend much time on limits. Okay, okay. We do not really have to spend much time on limits, on functions rather, because we still meet more of them in calculus, in all these limit problems. You know, calculus is like the combination of everything we've done before, like continuity, functions, and everything. So you need to understand all these functions, limits, continuity before you get to calculus. Because okay, for example, chain rule. When you want to apply chain rule, given a function f of g of x, this is a function of another function. So if you want to calculate this, chain rule implies that you differentiate the innermost function, derivative of g of x, and you also differentiate this f of g of x with respect to g of x. Don't worry, we get there soon. Because maybe thinking that how will we differentiate with respect to g of x? But I have a short method for doing this, and I've planned it, I've prepared it. We get there soon. Yes, that's a short method there's a short method for doing exponential functions. For example, e raised power of tan, sine, and everything. You just do it within a minute. No worry, you get it. Okay, let's just quickly check limits. When we're talking about limits, we understand that what is it? Okay. We understand that when we want to take the limit of a function, x is approaching c of f of x. F of x is the function. Now, it is not that lim f of x is equal to f of c under all conditions, but the idea is that x is not equal to c, but x is approaching c. X is approaching c. X is not equal to c. For example, look at this function. F of x is equal to x squared plus 1. Now, f of when we want to take the limit of f of x, limit of f of x as x is approaching 2, as x is approaching 2, or let's write it as lim x is approaching 2 of x squared plus 1. What we want to do now, we want to take the limit of this function, but you should observe that x is approaching 2, x is not equal to 2. Values that are approaching 2, like x is equal to 1.999, x is equal to 1.999. You know, the more you increase the number of 9, the more you get closer to 2. So x is equal to 1.999999. It is increasing. These values are increasing, and they are approaching 2. That's what we mean by lim x is approaching 2. When x is approaching 2 of x squared plus 1. Now, if you want to substitute these values, you know, this is for x, this is for x. Assuming we want to plot a graph, we have y equal to x squared plus 1. When you put values for x, you should observe the output also. Now, these are the values we are substituting for x, and the question is that we should calculate the output. That's why we want to calculate the limit of x squared plus 1. At this being that we want to calculate the value of x, then we can just conclude that it is within this range. But we want to calculate the output, we should observe the pattern. Lim x is approaching 2 of x squared plus 1 is equal to. So we want to observe the pattern. So when you substitute x with 1.999, you observe that you arrive at the output will be something like 4.999 when x is equal to 1.999. Then you will observe that the output will be something very close to 4.999. Also, when you put x equal to 1.999 this second, you observe that the output will be equal to 4.999. This also will increase. The output will be very close to 5. So it will continue like that. It will continue like that. Now, what we want to do is that we want to calculate the limit as x is approaching 2, as x is getting closer to 2. So you observe that the output is also getting very close to 5. That's why we always conclude that the limit as x is approaching this one is this. So now we can conclude that the limit as x is approaching 2, you know, these are the values. As x is approaching 2, the limit is equal to 5. And now we want to evaluate the limits in the normal way. Limit as x approaching 2 of x squared plus 1. Since there's no problem of indeterminate form or e raised power 0 or any form, then when we substitute the value directly, we have an output. When we substitute x equal to 2, that will give us 4. 4 plus 1, 5. So the answer is 5 here. Now we can observe it from this first principle that as x is approaching 2, the output is also approaching 5, getting very close to 5. Now we can calculate our answer here is 5. The same method applies for all other limit problems, but because there are some cases that it will be difficult to deal with them using this raw method. Let me call it raw method. This first principle. So you have to devise a shorter method, and from the theory of calculus, you're able to develop some theorems that would make it easier, like sandwich theorem, L'Hopital rule, and like simplification also. And another thing is that the L'Hopital rule we are even mentioning is an idea that was derived from first principle of derivation, like when you are differentiating using first principle. That idea was developed from it. But we won't be going into that one now. Let me look for another example. Okay. Now look at this. The limit as x is approaching 1 of 5x plus 4 minus 4 rather. So because there's no problem with this, let me add this. When you want to evaluate a limit and there's no problem of indeterminate or problem of when there's no other problem, like let me just say this indeterminate form is the basic problem of all limit problems. Even this one I will call infinity over infinity. You know, in limits, let's just assume that infinity is equal to 1 over 0. So 1 over 0 for the numerator, and this division sign divided by 1 over 0. So this division, when it comes to multiplication, they call it cross multiply. Then 1 over 0 times 0 over 1. Now we arrive at 0 over 0. So the basic problem is 0 over 0. Even when you're working with e raised to the power of when you're working with infinity times 0, infinity is also the same. You can assume that it's the same as 1 over 0 times this 0, then 0 over 0. So this is the basic problem. That's the point I'm trying to that's the point I'm trying to make from it. This is the basic problem, 0 over 0. So when you are working with a problem that is not giving something like 0 over 0, infinity over infinity, infinity times 0, 0 times infinity, e 1 raised to power infinity. 1 raised to power infinity is also a problem. 1 raised to power of infinity is the same thing as e. When we want to convert it to e, we write e raised to power of infinity then 1. You understand this? Okay, let me break it down. E, a number, a variable x can be written as e raised to power of ln x, since e and ln can still cancel out. When you're taking a function and its inverse together, they will cancel out. For example, we take log antilog 3, log antilog 3. Log will cancel the antilog, so it will give you 3. Now that's the same idea here. X is equal to e raised to power of ln x. E will still cancel out ln to give us x, and we say x is equal to x. So that's the idea. So this one, we want to apply this method. Please be careful of this method. It is very useful. It is very useful when you're dealing with limits, because there are some problems that would give 1 raised to power of infinity, and the only way you can, okay, don't let me say the only way, because there are some other ways. The best way you can go about it easily is by making this transformation. 1 raised to power of infinity is equal to e raised to power infinity ln 1. Now we know that ln 1 is equal to 0. So we have e raised to power infinity times 0. And infinity was assumed to be 1 over 0. So e raised to power 0 over 0. You see the problem now? Because of this indeterminate form, that's why we need to apply L'Hopital rule here also. Now let's go back to our basic problem. Then x is approaching 1 of 5x minus 4. So I said that when you are dealing with a problem, when you are dealing with a limit problem, and it is they call it continuous function that won't give you complexities, like limit as x approaches c won't give you f of c directly. They are functions that they are not regular functions. So when you are taking the limit as x is approaching 1 here, just substitute the value x equals to 1, 5 times 1 of 5 minus 4, 1. And I've explained how you can do this using the first principle, using the basic idea that as x is approaching 1, another thing you should take note of is that it is possible that x is approaching 1 from the left hand side. This is 1. On the plot, this is 2. It is possible that x is approaching 1 from this side. That's when we say x is 0.9, 0.99, 0.999, 0.999. They are all approaching 1 from the left hand side. And also it is possible that they are approaching 1 from the right hand side. From the right hand side. Then that one will be 1.0001. Then 1.00000. The zeros will increase. It is getting closer to 1.0 or 1. 1.00000 again. 1. So that's the idea. So that's another part that we don't need to consider now. They say since the left hand limit is not equal to the right hand limit, so we say that the limit does not exist. But let's leave that for now, because we've not treated that in the class, so that it won't affect in the exam. So just believe that when you're taking the limit, don't consider the left hand side or the right hand side for this basic class. So the limit of x is approaching 1 is equal to 5 times 1, 5 minus 4, and that is equal to 1. Another example is the limit of 7x plus 10. Now look at the way they even modify this question to make it terrifying. Lim x is approaching minus 3 of 7x plus 10. So the value x is approaching minus 3. When x is equal to minus 3, 7 times minus 3, minus 21 plus 10. Substitute minus 3 directly. Let's see what the output would be. 7x is equal to minus 3 plus 10. This is the absolute value. Don't remember that the absolute value is just for modifying the expression, that when you have plus or minus, it will still give you the output plus. For example, absolute value of minus 2 is equal to 2. The main role of that absolute value is to make our expression positive. Now, 7 times minus 3 is minus 21. absolute value of minus 21 plus 10. So this is equivalent to minus 21 plus 10, that is minus 11 in the absolute value, minus 11. So, and this is equal to 11. You know, I told you that the absolute value makes the input positive. Now, this is minus 11. When you take the absolute value, it returns to 11. Another example, name x approaches minus 2 of x squared x plus 1. Name the limit of x squared into bracket x plus 1 as x approaches minus 2. So what we need to do here is it is actually the same. So x is equal to minus 2. When you substitute it directly, it will give you a real number, numbers that can be found along the x-axis on the number line. So when x is equal to minus 2 square will give us 4 rather. So minus 2 plus 1, minus 1. And our answer is equal to minus 4. So that's all about these continuous functions. Okay, let's step it up a little. Let's look at functions that won't yield easily. Okay. Before that, let's look at this number 6 problem. Problem number 6. The limit as x approaches 1 of x minus 1 over x plus 2. One thing we should be mindful of is that we need to ensure that all criteria are being met before applying a certain rule. For example, someone may just look at this and conclude that because this is something f of x over g of x, maybe two functions, then the next thing is to apply L'Hopital rule. And when you apply L'Hopital rule, let's see what it will give us. X minus 1, when you differentiate it, will give you x, it will give you 1. Then x plus 2, when you differentiate it, will give you 1. Then the answer would be 1 if you apply L'Hopital rule. But in this case, we need to ensure that direct substitution gives 0 over 0 before we apply L'Hopital rule. Now let's see whether L'Hopital rule is applicable in this situation. When x is equal to 1, we have 1 minus 1 over 1 plus 2. And this is equal to 0 over 3 and equivalent to 0. The answer here is 0. This one is a little bit bad. Will you get on the location? Sorry, a minute. So the answer here is equal to 0. Now, the reason why this is not correct is that by direct substitution, the limit does not give 0 over 0. And the condition for L'Hopital rule is that if it gives 0 over 0, that's when you can apply the rule. But if the function does not give 0 over 0, you can't apply the rule. Now, using L'Hopital rule in this situation won't be right. Okay. Example number 7 also. Lim x approaches 3 of x minus 3 over x squared from the workbook. X minus 3 over x squared. So when you substitute the value directly, the limit directly, x equals to 3, you observe that 3 minus 3 is equal to 0 over 3 squared, 0 over 9. So the answer is just equal to 0, since there's no problem of 0 over 0, infinity times 0 or any other. Problem number 8. Let's see how it goes. The limit as x approaches minus 1 of x squared plus 1 over 3x squared minus 2x plus 5. Now, when x is equal to minus 1 square, that is 1. Then we have 1 over, maybe we should write this somewhere. Let's just assume that we're writing it somewhere, maybe at the back of our book. Minus 1 square is 1. So 1 over 3 times minus 1 square, and that is equal to 3 plus 2. You know, when x is equal to minus 1 here, the minus will affect the negative and it comes to plus. That's why I have plus 2 here. Then plus 5. We see that this gives 1 over 3 plus 2, 5. 5 plus 5, 10. And this is equal to 1 over 10. So, because this gives 1 over 10 without any complexity like 0 over 0, it means this method is valid. But using L'Hopital rule to solve something like this, when it does not give 0 over 0, would not be right. So, let's look at another example. Okay, let me just keep all this. I will assume that you understand how this work now, instead of just doing all this by substitution because of time. Okay, number 13. Number 13. Number 13 is also very interesting. The limit as x approaches 1 of x squared minus 1 over x minus 1. I told you before that at the point x is equal to 1, at the point x is equal to 1, the function will give 0 over 0. I told you that that the limit as x is approaching a certain number is not the function of that number. It is not always the function of that number, but it is the output as the no as the function is as the value the x is approaching that certain number. For example, x squared minus 1 over x minus 1. The limit as x approaches 1 can be written as, the values of x can be taken as 0.99, x equals to 0.999. And when you put in these values into the numerator and the denominator, you observe that the answer is getting close. It is increasing rapidly towards a certain number. It is approaching a certain number too. So when you substitute the values, x equals to 0.9, 0.99, 0.999, you observe that the output is also approaching a certain number too, as x is approaching 1, getting very close to 1. Okay, you may even be thinking that, okay, let's take it from the right hand side. Let's take it from the right hand side, going towards the left hand side, that x is equal to 1.0001. X is equal to 1.00001. X is, from this side also, it is also approaching 1. So we'll be taking that, okay, let's take it from this side. You will also observe that the value of 2 will also, the output will also be approaching 2 from the right hand side of 2, and that will be 0.0001, something like this, 2.00001. So you may take that as practice, maybe it's your calculator. So that's the first principal method. But you notice that at the point x equals to 2, at the main point where x is equal to 1, rather, you arrive at 1 minus 1 over 1 minus 1. So when you are drawing this type of plot, there are some graphs that when you are plotting this, you just, maybe this is the graph of the function. And at the point where x is equal to 1, the graph is moving, maybe it is moving in this direction. Then at the point x is equal to 1, you see that there will be something like, so there will be something there that you need, that there is something, there's a point there that is not very clear. I think I have the app that can plot the graph. So it will show you that at this point something is wrong. At this point something is wrong. You just circle this point, then move on. The reason is because at the point x equals to 1, it won't give you a number, but around it, you will notice that the value is approaching 1. Around it, the value is approaching 2. So because of this type of functions are the ones that give problem, that you can't evaluate them easily. But if you are good at all this algebraic simplification, then you can provide solution to this form of problems. And if you can, there are some advanced tricks also that you can make use of when trying to solve it. And you can also make use of all these series, express it in series. From there, you notice that continuously some parts of the terms will become 0. Then you get to answer easily. But for this basic class, we'll be considering L'Hopital rule for solving this type of function. Now, the condition for L'Hopital rule is that when we have 0 over 0, that is when we can apply it. And we see that actually this gives 0 over 0 when we substitute x equals to x with 1. So we can apply L'Hopital rule here. And when you apply the rule, you notice that x squared, when you differentiate it, will give you 2x. Because this is constant, we won't be giving attention to it because the derivative of minus 1 is 0. 2x over, when you differentiate x minus 1 also, it will give you 1. So when you put the value of x, the limit as x is approaching 1. When you put the value of x, which is 1, you know it will give you 2. So that's all about L'Hopital rule. Also, when you want to apply algebra to solve it, x squared minus 1 over x minus 1. And this is equal to, this x squared minus 1 is equal to x minus 1, x plus 1. Thank you. So x minus 1 over x plus 1 over x minus 1. So, okay. So x minus 1 cancels out and it gives x plus 1. So when you put the value of x, which is 1, 1 plus 1 gives 2. So that's all about that. Okay, let's just look at some critical examples. This is a famous integral. And this is a famous limit problem. The limit as x is approaching 0. The limit as x is approaching 0 of sin x over x. So when x is equal to 0, you saw that you have 0 over 0. So we can't solve this by elementary first. So we need to use the L'Hopital rule. And when you differentiate the numerator to give you cos x over 1. So now we have the limit as the limit of cos x as x approaches 0. Now when x is equal to 0, we see that there's no problem with it again. It gives 1. So our answer is equal to cos 0, which is equal to 1. So the limit as x approaches 0 of sin x over x is equal to 1. So with this, we can solve a wide range of questions. Like I saw one from the workbook. The limit as sin x over 2x. I think I saw it somewhere.
You're covering the lines.
I can't even find it again. Okay, this is number 24. Lim x approaches 0, then sin 2x over x. And mind you, it is not only in integration that we make substitution, we also make substitution here. In short, that's one of the tricks that we use when we are trying to break the bond of a limit problem. Now look at this case,
Yes.
sin 2x over x. We can convert this we can try to make this look like the problem we just finished solving. So you can just make the substitute of 2x with u. Let 2x with u. Let 2x be u. Then 2x is equal to u. And the problem becomes lim as x approaches 0. As x is approaching 0, it will also change the variable. It will change when you want to change this x also to u. It means to be representing the value of x, which is 0 here, with x here. So when x is equal to 0, 2 times 0 is equal to 0. Then u is equal to 0. Lim u is approaching 0. Sin 2x. Now 2x is written as u. 2x was written as u in this case. So sin u over. Now x will be equal to what? No, this is 2x equal to u. Then x will be equal to u over 2. U over 2. And this is equal this is division. When you perform the division properly, sin u divided by u over 2. And this will become 2 over u. Then sin u times 2 over u. And this is equal to 2 sin u over u. So you observe that 2 will come outside. Then the limit as u approaches 0 of sin u over u. So the problem becomes 2 lim u approaches 0 of sin u over u. And we already have this as 1. Limit as x approaches 0 of sin x over x. Don't care about the variable there. This x could be u, could be t, or any other variable. So sin u over u is also equal to 1 as the limit is approaching 0. So we can conclude that our answer is 2 times 1, which is equal to 2. So that's the answer to the limit problem. Another one, number 25. The limit as x approaches pi of 1 plus cos x over x minus pi square. So when x is equal to pi, we see that it gives 1 plus cos pi over x over pi minus pi square. So cos pi, we know that cos pi is equal to minus 1. So 1 minus 1 will give 0 over pi minus pi, 0 square, still 0. So we can apply the L'Hopital rule here. Now the definition of L'Hopital rule is that when a function, the limit of a function as x is approaching c, f of x over g of x is equal to the limit as x is approaching c of f complement of x over g complement of x. It means the derivative of f of x and the derivative of g of x. And this is only true when f of c gives 0 and also g of c gives 0. What I mean by f of c and g of c is that by direct substitution, f of c, when you substitute f of c, when you substitute x with c here, f of 0, it gives 0 over g of c, which also gives 0. Then this is just a technical way of writing, saying that when your function gives 0 over 0, then you apply the L'Hopital rule. For example, in this case, this is our c. So function of c, f of x is the numerator here in this case. So f of c, function of c, function of pi in this case. Function of pi gives 0. Then the g of pi also gives 0. That's why we can think of the L'Hopital rule that we differentiate the numerator and the denominator separately. So people used to make that mistake. They would differentiate the numerator and the denominator directly using quotient rule. So that's what we write. So you need to take care of, you need to be mindful of that also. The L'Hopital rule is that you differentiate the numerator and the denominator separately. Then this problem gives, when you differentiate this, it will give you minus sin x. The derivative of 1 is 0, and the derivative of cos x is equal to minus sin x over, when you differentiate this, 2 will come to the back, and you have x minus pi. So when x is equal to pi, sin pi itself is equal to 0. Let's write it somewhere. Sin pi is equal to 0 over, when x is equal to pi minus pi is equal to 0. Then we have 0 over 0, which also needs the L'Hopital rule. So you also need to note that when you are working with the L'Hopital rule, or when you are working with a problem, that after applying the L'Hopital rule, it gives 0 over 0. Then you can still apply it again. You can apply it you can just apply it as much as possible. Just ensure that you break the bond of the problem. For example, this case, e raised power of x over x raised power of 100. The limit as x is approaching infinity. Maybe this is what we do now, so that you see how it works. The limit as x is approaching infinity. Okay. So in this case, this gives 0 over 0, and I said that you need to apply the L'Hopital rule again. So applying the L'Hopital rule to cos x, it will give you, let's first put this limit as x approaches pi. Then it will give you, when you differentiate this minus, it will give you cos x, but minus is here, so we write minus cos x. And when you differentiate this also, when you differentiate x minus pi, it will give you, this one will turn to 1. So 2, just 2. So the limit as x approaches pi, cos pi is equal to minus 1. So because we have minus here before, it will just turn to 1. Then over this constant 2. And that's our answer. So just understand how to go about this. Understand that when you have 0 over 0 or infinity over infinity, then you apply the L'Hopital rule, or 0 times infinity, infinity times 0, or in any other form that contains 0 over 0. Then you apply the L'Hopital rule to that specific part that has 0 over 0. Oh, this is a very interesting problem. Okay, I said I want to consider this. Okay, let this come before that. The limit as x approaches infinity of x raised to the power of 1 over x Now this problem, by direct substitution, we see that it gives infinity, this is infinity raised to the power of 1 over infinity, and 1 over infinity is equal to 0. So this 1 over 0, infinity raised to power 0, we need to be sure that it contains 0 over 0 before we just conclude that this is arbitrary. So first represent this infinity raised to power 0 in the form of e raised to power 0 ln infinity. Ln infinity is equal to infinity. So 0 times infinity is actually a variance of 0 over 0. So we can conclude that this will also entails, so write it as ln x approaches infinity of e raised to power 1 over x ln x. So this is equal to ln x approaches infinity e raised to power ln x over x. Do you understand the process? Understand the process here. 1 over x ln x is the same thing as writing ln x over x. So from this part, we need to substitute the value of x and see the part that gives either 0 over 0 or infinity over infinity. So when you substitute the value x equal to infinity, it gives ln infinity, which is equal to infinity over x, which is infinity. So infinity over infinity, it means we can apply the vector rule to this numerator and to this power rather. So you can just bring down this power that we want to consider the limit as x approaches infinity of ln x over x separately. So because this gives infinity over infinity, it means we can apply the L'Hopital rule. So when you differentiate the numerator, the derivative of ln x, it will give you 1 over x over the derivative of this x, which is just 1. And this is equal to the limit as x approaches infinity of 1 over x. So you can directly substitute the value of infinity now, 1 over infinity, and this is equal to 0. This is equal to 0. So that's just the answer to this problem. If there's anyone you think that we need to solve together, you can just comment it. But before that, okay, the limit as x is approaching infinity of e raised to power x over x is 100. X is approaching infinity of e raised to power x over x raised to power of 100. So x is equal to infinity. We say that it gives e raised to power infinity is infinity. The rule is that any number a raised to power of infinity is equal to infinity if a is greater than 0, or equal to 0 if a is less than 0, and at the point 0 it is equal to minus infinity. It's equal to minus infinity at the point a equals to 0, if my observation is right. So e raised to power x x raised to power of 100 is equal to, because this gives infinity over infinity, e is greater than 1. E is greater than 1. It has a value close to 2, 3, within 2 and 3. So we can conclude that a number greater than 0 will give infinity when we raise a power of infinity to it. So e raised to power infinity is equal to infinity over infinity raised to power 100, which is equal to infinity. So we can apply the L'Hopital rule here again. The x approaches infinity. So when you differentiate the numerator here, you see that you still give you e raised to power x. You know that e raised to power of x is a stubborn function, that when you differentiate it even 100 times, 200 times, it will remain the same. And when you differentiate x raised to power of 100, it will give you 100 x raised to power of 99. We see that the same again when we substitute the value infinity with it, it still give us infinity over infinity. So it means that's not the end, that we still need to apply the rule again. And you will notice by observation now, okay, let's do one more before we observe. The limit as x is approaching infinity, e raised to power x over 100 x raised to power of 99. When you differentiate it again, it will give you, 100 is there before, times this 99 that will come down, 99 x raised to power of 98. So this is again another function that is equal to infinity over infinity by direct substitution. E raised to power x over 100 times 99 x raised to the power of 98. So when x is equal to infinity, we see that it gives infinity over infinity again. So the observation I was trying to bring in was that at the when you continue differentiating it, we see that this numerator is not changing. This numerator is not changing. It's only the denominator that is changing. So when you continue this process again, when you continue it, when you continue when you perform this process in about 100 times, you observe that this power will be coming down, 98, 97, and it will become something like 100 times 99 times 98 times 97 times 96 times 95. So this function gives e raised of x over 100 times 99 times 98 up to the point where x is equal to 0, where x is equal to 1. Let's start with where x is equal to 1 first. Then up to times 2x. Let me bring it down again. The limit as x is approaching infinity, e raised by x over 100 times 99 times 98 up to times 2x. So again, we see that this is the last step now. E raised by x over 100 times everything times x. Now we apply the rule again. When you differentiate it, look at that rule again one more time. When you apply look at that rule again, to give e raised by x over, and this x will vanish, it will give you 1. So 100 times 99 times 98 up to times 2 times 1. We can conclude that this is just 100 factorial. Now we want to take the limit as x approaches infinity of 1 over 100 factorial and this e raised by x. Now 1 over 100 factorial is a constant. So it is just like we want to take the limit of e raised by x alone. The limit as x approaches infinity of e raised by x is equal to e raised by infinity. And we know that e raised by infinity is equal to infinity because e is greater than 2. So it is because e is greater than 0, it's equal to infinity. So we can conclude that the answer to the problem, the next approaches infinity, e raised by x over x raised by 100 is equal to infinity. Now look at a similar problem. A similar problem. The limit. Sorry. I just discovered that some people have mentioned some numbers that needs to be treated. Okay, number 27, number 28, number 33. Okay, we do everything together. So, okay, let's first treat this case where x is equal to minus infinity. Where x is equal to minus. Okay, we can say x is approaching minus infinity or x is minus. They are both the same. So, e raised to the power of minus x over, when we write minus x raised to the power of 100 years, it's still the same thing as x raised to the power of 100. So let me just write x raised to the power of 100. So this is when we apply L'Hopital rule. Or is there even you need to ensure that the condition is being met before we apply L'Hopital rule. So let's check. At x equals to infinity, e raised to the power of minus infinity over at x equals to infinity is 100, and this is equal to e raised to the power of minus infinity is equal to 0 over infinity. We need to be sure that this is indeterminate or not before we take any step, because you can just look at this and conclude that because it looks like one of all those complex, like they call it 7 deadly sins, because it looks like one of them, then we say it is indeterminate. No, you need to be sure of it. This is 0 divided by infinity, and I said that infinity can be written as 1 over 0. So when you cross multiply this, 1 over 0 becomes 0 over 1. 0 times 0 over 1, and this is equal to 0. So it means that when we perform direct substitution, e raised to minus infinity over x raised to the power of 100 gives 0. So our answer is directly equal to 0 here. So another person might have just bumped into differentiation that no, this one is L'Hopital rule, but you need to observe before you perform any step. Oh, there are a lot of comments here. Someone said that I should say something about left hand side and right hand side limits. Okay, the left hand side limit. A limit a limit exists if limit as x approaches c minus. C minus here means that it is approaching from the left hand side of f of x. F of x is the function. Then if this is equal to the limit as x is approaching infinity, as x is approaching c rather from the positive axis of f of x, then the limit exists. Then the limit exists. But if these are not equal, the left hand side limit and right hand side limit are not equal, then it means that the limit does not exist. We call it limit DNE. The limit does not exist. Okay, this is one that we can. I don't want this to lead to confusion because in math 1 class, we were told that the limit as x approaches 0 of 1 over x is equal to infinity. But I believe that this is just for the level we are. But when you want to consider it in the most appropriate way, the limit does not exist in this case because as x is approaching 0 on the negative and on the positive axis, they are not equal. Look at this. This is 0. X is approaching 0 from this side. We know that this side is negative. And this is the positive part. The positive part. So it means that as x is approaching 0 on the positive part, all the values we'll be getting are positive numbers, positive, positive, positive. And it is like when you continue the process, you discover that it's equal to positive infinity. And also when let me put this, x is approaching 0 from the positive part is equal to positive infinity. And when you observe the limit as x is approaching 0 from the negative part also, from the negative, you observe that everything you be getting here negative, 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 like minus 1.5 minus something, something, something. So negative, negative, negative. And this will also give you minus infinity. So because the limit on the right hand side is not equal to the limit on the left hand side, we say the limit does not exist. The limit as x approaches 0 from the positive axis of f of x is not equal. Is not equal to the limit as x approaches 0 from the negative axis of f of x. So we say that the limit does not exist. Limit DNE. Limit does not exist. But we have many cases whereby the limit exists. Like all this one we've been dealing with, there are cases where the limit exists. Let me look at another one again. Number 27. Someone said we should do it number 27. Oh, I can recall that this number 27, we have to apply the vector rule about 6 times. So, okay, let's do it together. Just one thing about this topic is that understand what you want to do. Just looking at it, you want to know what to do, but until you put in some tests, like first test with x equals to 0 to see how the output will be. When you put x equals to 0, you see that, okay, this is what it gives. Then this is what I should do. If I want to make it to form a function that will easily take in the vector rule. So that's one thing you should also observe. Another thing is that a function will just become very big that when you just put in direct substitution, you see that it is something that you just need to put in the values to get the answer. It won't lead to any complexity of rational functions that will give you 0 over 0, 1 over 0, any other thing like that. So number 27, the limit as x approaches 0, as t approaches 0. Okay, let's use x. You can still use x. X tan inverse of x minus sine square x over x raised to the power of 6. Okay, so let's first put in the value of x to see if there's no problem with it. At x equal to 0, tan inverse of 0 is equal to 0. Then 0 times tan inverse of 0 gives 0 minus. At x is equal to 0, sine square 0 is equal to 0 over the denominator, which gives 0. So this also gives 0. So we can apply the L'Hopital rule here in this case. So when we differentiate this, the problem is that we know that when this gives 0/0, how to go about it is to differentiate the denominator and the numerator separately. Now, another problem that we can find in this problem is that when we want to differentiate the numerator itself, it's a problem that should be considered separately. So when you differentiate the numerator, u dv dx, this is product of two functions. It means we apply the product rule. And this one, just differentiate it with chain rule, depending on the method you best understand. So people can just take can introduce natural evidence to this one to break it down. Or any other way differentiation is something that you can do in many ways. You can do differentiation in many ways. The same also integration, you can do it in many ways. That's why integration and differentiation appears to be one of the most interesting parts as for me, most interesting parts. Because you can do it in many ways. A single integral problem, a single differential problem could be solved in like 6 methods, 7 different methods, 7 different ways. So you need to understand this. So when you differentiate this one, x u dv dx plus v du dx, I assume that this is something you can just do. U dv dx, the derivative of tan inverse of x is 1 plus x squared plus v du dx. The derivative of this one is just 1. So I'll just write tan inverse of 1, tan inverse of x. Note that this expression is just for this first part. So for this second part, when you differentiate this sin square x, you have 2. This 2 will come to the back. Sin x cos x. I want to shorten this. I'll just write sin 2x directly because this 2 sin x cos x is equivalent to sin 2x. So that's for the numerator over the denominator. When you differentiate this x raised to the power of 6, to give you 6x raised to the power of 5. 6x raised to the power of 5. So let's simplify this. The limit as x approaches 0 of, so when you distribute this x raised to the power of 5 to each, you observe that we have 1 over 6 x raised to the power of 5 into brackets x raised to the power of 4. 1 has been cancelled here, so we are left with x raised to the power of 4. Then 1 plus x squared plus tan inverse of x over 6x raised to the power 5 minus 2, or let me just write sin 2x. 2 sin x cos x is still the same thing as sin 2x. Sin 2x over 6x raised to the power of 5. So from here, let's see if any part will cancel out easily. Tan inverse of 0 over 0, sin 0 over 0, this will cancel out easily. So, okay, maybe there's even no need of simplifying further. Let's just leave it as it was with the initial problem. Okay, let's bring everything back. I was saying if that would be a good idea to split everything, but we see that it won't give you something accurate. We give you something like, if you continue with it, will give you something like 1 over 0, and that won't be defined for this type of problem. So 1 plus x squared plus tan inverse of x. If there's any logical thinking about this, it is possible that you'll be able to solve this in less than just 1 page. There's any way you can think about it logically. So x raised to the power of x over x is, okay, x is 4 of 4. This should be 1 then. Then over 6x raised to the power of 5. Something is wrong here. Okay, this x should be there then. Remove this. I'm returning it back to this former state. Only this will change. Only these 2 sin x cos x will change to sin 2x. Let me make it more accurate. The limit as x approaches 0 of x over 1 plus x squared plus tan inverse of x minus sin 2x over 6x raised to the power 5. So from this step, let's substitute the value 0 again and see what the output will be. When x is equal to 0, we notice that this part will become 0. Tan inverse of 0 is also equal to 0. Sin 2x is also equal to 0. Wow, the numerator gives 0. Now the denominator also gives 0. 6 times 0 is 0. So let's apply the L'Hopital rule again. This is another problem again because we want to differentiate the numerator. For this part, we use quotient rule. Okay, let's go. As x approaches 0. I don't want to spend much time doing the differentiation. I believe that is something you can do. Quotient rule for this one, v du dx minus u du dx over v square. So v here is 1 plus x square. So 1 plus x square du dx. This one will give 1. So I won't write anything. Minus u du dx. This one will give you 2x. So 2x times that u, it will give you 2x square over v square. That is 1 plus x square square plus, when you differentiate tan inverse of x, it will give you 1 over x, 1 plus x square. Use 1 over 1 plus x square minus, when you differentiate sin 2x also, it gives 2 cos 2x. It gives 2 cos 2x. Just understand the step. That's the most important. So when you differentiate this also, it gives 5 times 6, 30 x raised to the power of 4. So from this step, we need to test again to see if it's something we can do easily. But if not, if it still gives 0 over 0, then we apply the L'Hopital rule again. But before that, okay, someone is asking like, why are you differentiating a limit question? That's the procedure when you are trying to solve a problem involving 0 over 0 that gives 0 over 0 by that substitution. I've explained earlier that L'Hopital rule states that we differentiate the numerator and the denominator separately. But in this case, the denominator now tends to be another case that should be opened in a differential problem. But just understand that, just if you just understand the limits of if you just understand this L'Hopital theorem, then you'll be able to do, don't mind how obfuscating this look or how big it looks. Just understand that you differentiate the numerator and differentiate the denominator, and that's everything I've been doing here. And that's, if you really understand all these things, you will see any mathematics problem and you won't be able, you won't even be thinking that this one is hard, this one is easy hard, when you understand what you want to do. Like the question Dr. Gray gave in the second test, there's a problem like laying 2 to minus x plus lame the limit of 2 to minus x minus 2 to minus x raised to the power of, okay, lame is here, natural logarithm of raised to the power of the same. So if you really understand L'Hopital rule, you will notice that no matter how long the expression looks, everything you need to do remains the same. Just substitute, simplify, and apply the rule when it wherever it is needed. Just apply it. So just understand how to do it. Now in this case, 30 is a constant. Let's bring it out. 1 over 30 lame x approaches 0. Let's expand this numerator to simplify the problem a little. So 1 plus x square minus 2x square over 1 plus x square square plus 1 over 1 plus x square minus 2 cos 2x, everything over x raised to the power of 4. Now this is equivalent to 1 over 30. Now I'm trying to simplify so that when we want to apply the L'Hopital rule, we won't be applying it in a function that needs to be simplified and we'll be giving something very complex. But when we simplify it to the least, they'll be able to apply it effectively. So 1 over 30 lame x approaches 0. So 1 minus 2 here, it will give 1 minus x square over 1 plus x square square plus 1 over 1 plus x square minus 2 cos 2x over x raised to the power of 4. Now we can just take the LCM of this because they look alike. So when you take the LCM, let me just inspect and see what it will give. You give 1 plus x squared over 1 plus x squared squared. This will give 1 plus x squared, 1 plus x squared plus 1 minus x squared over 1 plus x squared squared. So when you take the LCM, it will give 2 over 1 plus x squared squared. So this is equal to lim 1 over 30 first. Lim x approaches 0 of 1 of 2 over 1 plus x squared squared. Then plus 1 over 1 plus x squared. Oh, sorry, we simplified this to give 2 over 1 plus x squared squared. Then minus 2 cos 2x. Now, this is just the numerator over the denominator, which is x raised to the power of 4. This is a little bit simplified now. So if you want to apply the L'Hopital rule, you know that we only be applying it to these two expressions, not something very big like the former. But we can still simplify this further. Or let's write this as 1 over 30 lim x approaches 0. 2 is even constant and 2 is common here. So let's bring out 2. Sorry, 2 should be here. 2 over 30. So lim, I can write this as, no, 2 is out now. I have 1 over 1 plus x squared. So I can write it as 1 plus x squared raised to the power of minus 2. I believe that this is well understood. Minus cos 2x over x raised to the power of 4. Now the problem is a little bit simplified. Let's apply the L'Hopital rule again. 2 over 30 is 1 over 15. Lim x approaches 0. But before we apply the L'Hopital rule, let's be sure that it is something you can apply it with. At x is equal to 0, 1 raised to the power of minus 2 is still 1. So 1 minus cos 0 is 1. 1 minus 1 is 0. 0 over 0. L'Hopital rule again. We need to differentiate this. So when you differentiate this, I will assume that you know how to do all this using all these questions and products. So you should get, when you differentiate this, minus 4 x into bracket 1 plus x squared is power of minus 3. So when you differentiate this cos 2x also, it will give plus 2 sin 2x. When you differentiate cos, it will give you minus sin. But we have minus here already, so it will give you plus. So that would come out when you differentiate cos 2 something. Then bring that out 2. That's why we have 2 sin 2x here. So for the denominator also 4x raised to the power of 3. So what is common again? Minus 4 and plus 2 here. Can factor out 2. Oh, the 2 that we want to factor out will divide this 4. Will be simplified with this 4, and it will give us 1 over 2. So we can bring out 1 over 2. 1 over 30. 1 over 30. Lim x approaches 0 of sin 2x minus 2x into bracket 1 plus x squared minus 3 over 2x raised by 3. One thing I should be mindful of is that when you are doing this type of long question like this, like there are some problems that you may encounter along the process of solution. Like differentiating this one now, if you omit just a very small number like 2 or just a negative sign, it could affect the final answer. So we need to be careful while doing this. So if you observe any mistake, also you can call my attention to just comment. I think I'm following up with the comments also. So by direct substitution again, when x is equal to 0, sin 0 will give 0, then minus 2, because this x that is leading, when it turns, because of this x that is leading, when it turns to 0, then everything here will turn to 0 also. 0 minus 0 again over 0. So we apply the capital rule again. 1 over 30, then x approaches 0. So when you differentiate that sine 2x, it gives cos 2x. It gives 2 cos 2x minus. Now this is another problem again. You need to differentiate this, and this can be differentiated using product rule. But if you like, you may convert this 1 plus x squared raised to the power of minus 3. So 1 over 1 plus x squared raised to the power of 3. Then you would have to use quotient rule. But sometimes I told some people in the past that a function that can be represented in the form of quotient can also be solved using product rule. Look at this example now. Sine, okay, let me use, okay, sine x over e raised by x. Now this should be solved using quotient rule, but you can also express it as product rule. That is sine x e raised by minus x. So you differentiate u dv dx plus v du dx, and I think this one is even simpler than applying the quotient rule here. So that's something you can. That's something I want to do here also. X into brackets 1 plus x squared minus 3. I want to differentiate it using quotient, using product rule. Hey, there's an issue here. Please, we would have to cut this now. I will be back in a jiffy. I will get connected back. I'm so sorry about that. The phone is very big. So this is just the process. Let me quickly summarize this step. You just differentiate this using quotient, using product rule. My phone will switch off now, and you differentiate this also. So you will check again. Just ensure that all processes are correct. Sorry, I want to set the connection. I don't know how to. Trying to. Okay, sorry for the inconvenience. Now I'm using a power bank. I hope this one would help. Okay, so we stopped here, and okay, let's start from this place. I said that from this side we need to apply the capital rule again since it gave 0 over 0 when we tested it. Now differentiating sine 2x, we got 2 cos 2x minus 2. Now we need to differentiate this using product rule. So x would come first, then you differentiate the second. You differentiate 1 plus x squared raised to the power of minus 3. Let me try my idea. So it will give you 2x. The inner one will give you 2x, then minus 3. 1 plus x squared raised to the power of minus 4. Okay, let this one become bigger because the 2 is outside everything. Then when you differentiate, this is u dv dx, u dv dx plus v. Our v here is given as 1 plus x squared raised to the power minus 3. 1 plus x squared raised to the power minus 3 du dx. This is just 1, so I won't put anything. And let's close the brackets. Over this 2x raised to the power 3. When we differentiate it, it gives 6x. Then we close the whole bracket. So this is the expression we get. Let's simplify this before we know what to do next. This is equivalent to 1 over 30. Let's bring out these two. This 2 is common to everything here. So let's bring out 2. That is 2 over 30 lim. Sorry, I want to set the messages in order. Live chats. Okay, so I can see it now. So lim x approaches 0. Now 2 is no longer in, cos 2x minus 2 minus, when 2 is no longer there, we factorized out the negative, the 2. So this minus, let's multiply through. When we multiply this by minus 1, so we arrive at, minus is here already. So minus times minus will turn to plus. And this will be having 3. Plus for this first one, plus 3x squared. That x squared is from this x and x squared into brackets 1 plus x squared raised to the power of minus 4. Then this second part, this minus 2 is for everything. Okay, don't let us even mention 2 again because we factorized out 2 and 2 is here. So let's multiply this one by minus 1. So that minus 1 will make it minus 1 plus x squared raised to the power of minus 3. Then everything over 6x. So this should be x squared because when we differentiate 2x raised by 3, we arrive at 3x squared. We arrive at 6x squared rather. So this should be 6x squared also. This sounds to get disconnected. Okay. So by simplifying this leading coefficient, we have 1 over 15. 1 over 15 lim x approaches 0. This 6 outside, we should even factorize this. So let's just put it here. Maybe 1 over 6 here times cos 2x plus 3x squared 1 plus x squared raised to the power of minus 4 minus 1 plus x squared raised to the power of minus 3 over 6 over x squared, which is equals to 15 times 6. And 15 times 6 can 15 times 6 gives 90. Okay, so we have 1 over 90 lim x approaches 0 of cos 2x plus 3x squared 1 plus x squared raised to the power of minus 4 minus 1 plus x squared raised to the power of minus 3. Everything over x squared. Let's check it. Let's check again. At x equals to 0, cos 0 gives 1. Then when x is equal to 0 here, everything here becomes 0 minus. When x is equal to 0, we have 1 again. So 1 minus 1 gives 0 and the 0 here. So we need to apply the L'Hopital rule again. This is actually a stubborn function that we need to apply the L'Hopital rule about 6 times. I could recall that the one we did in the assignment also, I applied it about 6 times with some ideas to simplify the expression. But in this way, I'm just trying to bring out everything so that there won't be any mistake in maybe the simplification. So 1 over 90 lim x approaches 0. So when we apply the L'Hopital rule again, we differentiate this, it gives minus 2 sine 2x plus 3x squared. So we differentiate this 1 plus x squared raised to the power of minus 4. And it gives 4 times 2. It gives minus 4 times 2, 8x into brackets 1 plus x squared raised to the power of minus 5. When we just trying to differentiate this using product rule, I believe you can do it. So you can do it somewhere. If you feel like this is not very clear to you, you can do it somewhere. So 3x squared. When you differentiate this, we have 2x times 4 minus 8x into bracket 1 plus x squared raised to power minus 5. Okay, that's all for the first part. Plus v du. This one will give us 6x. 6x into bracket 1 plus x squared raised to power minus 4. Oh, this side won't be sufficient. Okay, over. And we differentiate the denominator, so we have 2x. Okay, let's continue it here. This part, when you differentiate this part also, minus, okay, to give you plus, because the minus 3 up times this minus is to give you plus. Then the 3 times the 2x give you 6x into bracket 1 plus x squared raised to power of minus 4. Okay, remember that this one is also having over 2x. So let's even see if we can apply. Maybe it will directly give us the answer now. When x is equal to 0, sine 0 gives 0. So everything here becomes 0. When x is equal to 0, everything in this bracket becomes 0. When x is equal to 0 here, this gives, okay, x is outside here, so 0 times anything here will also give 0. When x is 0 here, this one will also give 0 over 0. Okay, let me open this on a new page and see what we can do to it, because we won't know what we can do until we bring it out and we look at it. 1 over 90, the limit as x approaches 0 of, okay, 2 sine 2x minus 2 sine minus 2 sine 2x plus 3x. Okay, let's expand this. So 3x squared times minus 8, 3x squared times minus 8x times minus 24x raised to power of 3 minus 24x raised to power of 3 into bracket 1 plus x squared raised to power minus 5. 1 plus x squared raised to power of minus 5 plus 6x, 1 plus x squared raised to power minus 4 plus 6x into bracket 1 plus x squared raised to power of minus 4. Then the last part, plus 6x into bracket 1 plus x squared raised to power minus 4. Cool. Plus 6x 1 plus x squared raised to power minus 4. How true is this? It says a mistake there. Anyway, 2x, everything over 2x. Now let's check this again. It seems like something is fishy here. When you differentiate this, 3x squared into bracket 1 plus 4 times 2 minus 8 to bracket 1 plus x squared is minus 5 plus 1 plus x squared is minus 4 plus 6x minus, okay, plus 3 times 2 6x into bracket 1 plus x squared is minus 4. Okay, I think that's right. So from this step, we've checked and we discovered that it is, okay, we can even simplify this 6 into bracket 1 plus x squared minus 4 plus 6x into bracket 1 plus x squared is minus 4. We can simplify it, so we can write it as 1 over 90 lim x approaches 0 into bracket minus 2 into bracket, when we bring out 2 can be simplified with these 2. So 2 we divide everything through and we have minus sine 2x minus 12x cube to bracket 1 plus x squared raised to the power of minus 5 plus, these are the same functions. So when you sum up these two functions, they will give 12x. So when we divide through by that 2, so this will also give 6, 1 plus x squared raised to the power of minus 4. So everything over x Now, I don't think we need to apply the L'Hopital rule again because we already have the standard solution. Now, minus sine 2x minus sine 2x over x. It is something we've discussed before. Minus sine 2x over x. When I was explaining how to this sine 2x over x, we got 2 for it. We got 2. So it means sine 2x over x is equal to 2. Equal to 2. So because minus is outside, we write minus 2. So this x cancels 1 here. And when we put x equals to 0, everything here becomes 0. Everything here becomes 0. And when we put x as 0 here, this one becomes 6. So we have minus 2 for this one plus 6 here. So if there's no mistake, it should be 1 over 90 into bracket 4. But I said that there's a mistake somewhere because the process of solution was not very neat. So you can just follow the process. That's the process to do it. Just ensure that there's no mistake there. This gives 2 over 45 when simplified. Whether this is the answer or not, just ensure that you understand the process of solution. So the first step is to check with the value 0. When you substitute the value 0, you discover that you see that this one gives 0 over 0. So because of that 0 over 0, we applied the L'Hopital rule. But in this problem, we applied the L'Hopital rule about, is it not 5 times? So we should always be careful. Maybe in the exam or anywhere when we are working with this type of problem, that is why we should be more careful with how we are solving the problem, because any small mistake in the exam that thing happened in the second test. So any small mistake would affect everything, and in the process of trying to solve it again, the time might elapse. So you need to be careful while you are trying to solve a problem that you know that this one is very long. If it is just a very small problem now, you could be careless about that because you know that in a jiffy it is something you can quickly retrace your step and do again. But something as long as this, just be careful with it. And it is even possible that you leave it for any other question, then come back to it so that it won't while away time. Okay, now let me look at another question from the comments. Question 27. Question 27. Okay, the one we discussed is question 27. Just I believe that you understand how to go about the 27. The answer might not be correct, but just understand the solution step. Question number 28. Okay. Wow, 20. I think that 27 is even the problem with the most difficult problem in this series. So 28, the limit as x approaches infinity of ln x over ln x. For that problem number 27, the solution I made in the group, you can also check it up. I believe that with this idea that you have from this explanation, if you juxtapose both, you should be able to provide solution to it. I made the solution in the group, so just check it. When you check the solution and you compare both, you will see where the mistake lies. Maybe when I was trying to differentiate and I omitted a 2 or the sign. So that's usually the most common mistake in this type of problem. So let's solve this limit. Limit of ln x over ln x as x approaches infinity. This can be solved in many ways. We know that. Okay, let's first check before we even talk about the method we would use. When x is equal to infinity, ln infinity is infinity, and the ln of that infinity also is equal to infinity. So the numerator gives infinity. The denominator ln infinity is equal to infinity. So because of this, we can rather apply the L'Hopital rule. And L'Hopital rule said that we differentiate the numerator and we differentiate the denominator. If we want to apply that method, we just need to write ln x approaches infinity. So we differentiate the numerator. The derivative of this ln x is, when you differentiate this, if you open it in another page and you differentiate it, you get 1 over x ln x. And when you differentiate this denominator also, ln x, it will give you 1 over x. to give you 1 over x. So we have lim x approaches infinity of 1 over x ln x divided by 1 over x. Let me open it here. The limit as x approaches infinity of 1 over x ln x divided by 1 over x, or we write times x over 1. So when we multiply it by x cancels here. Then it gives the limit as x approaches infinity. The limit as x approaches infinity of 1 over ln x. So when x is equal to infinity, 1 over infinity gives 0. So this is a very direct method. The answer is equal to 0. What the process of solution is that from the beginning, lim x as x approaches infinity, ln x over ln x. So we first checked to be sure that we can apply the L'Hopital rule. When x is equal to infinity, ln infinity gives infinity. So infinity over infinity, because of this infinity over infinity, we apply the L'Hopital rule. When you differentiate ln x, you will arrive at 1 over x ln x. Okay, if you want to know how I did this by observing, so you first differentiate this ln x, it gives 1 over x. Then you assume that you are differentiating ln u. So when you differentiate ln u, you also get 1 over u. But now we want to stop assuming that so u is now back to its real position, ln x, 1 over x ln x, everything over, and differentiate ln x 1 over x. So, and by simplifying and substituting the value, we arrive at 0. Okay, let me introduce another method for this one. There's another method we would love to use to solve this. The problem again. The problem is ln x as x approaches infinity. You can post more questions. So ln x over ln x. Now let ln x equal to u. Use the substitution method that I introduced in the first part of this lecture. Let ln x equal to u. When ln x is equal to u, then the limit will also change. X is infinity. When x is infinity, ln infinity will give infinity. So ln u without be approaching infinity. Ln x is already equal to u. Then ln u over u. And if you like, you can write this as let's use x infinity, ln x over x. And this is very cheap. When you use the L'Hopital rule, you differentiate by direct substitution, it gives 0 over 0, infinity over infinity, a variant of 0 over 0. So we can apply the L'Hopital rule efficiently or effectively. So when you differentiate it, ln x approaches infinity, denominator will give 1 over x over the denominator, which gives 1. So the problem becomes the limit as x approaches infinity of 1 over x. And when x is equal to infinity, 1 over infinity gives 0. So the same answer we got for the first, the same answer we got for the second. So the main idea about this topic is about these courses, that you should understand what you are doing. You should understand. You can use any method. Just understand that the method you are using is right. Another person may decide to substitute everything here, ln x with u. Then the person would substitute it and still arrive at a correct answer. So that's it. Is there any other question I would love to post? Okay, somebody said question 33, number 33. Okay, this is number 33. You want to calculate the limit of x as x approaches infinity. As x approaches infinity, so square root of x squared minus x plus 1 minus square root of x. But before we proceed, something you should understand. I told you before that 0 over 0 is indeterminate. Infinity over infinity is indeterminate. Infinity raised to power 0. infinity raised by 0, the infinity raised by 0 is also indeterminate, and there are many expressions in that form. 0 times infinity is also indeterminate. But I want to tell you also that infinity minus infinity is indeterminate, and we can conclude that indeterminate is just a way of saying that we can't determine the answer, we can't conclude the answer, because maybe the answer is very, like, it varies with the question given. For example, we know that in telescopic series in math 101, infinity minus infinity could give a real number and it could give infinity. So it depends on the problem we are working with. So infinity minus infinity is also equal to indeterminate. It's also indeterminate. Now, this is indeterminate, and we can prove that by writing E, by using E and lin, this E and lin together. I told you that when you put E and lin together, it's the same thing as lin and E together. So when you put lin and E together of infinity minus infinity, you will notice that this is the same thing as ln e raised by infinity over e raised by infinity. So e raised by infinity is equal to infinity, and e raised by infinity is equal to infinity. So infinity over infinity is equal to, is something we can't conclude, is indeterminate. So we can say that infinity minus infinity is also indeterminate. So because if you put x equals to infinity here, in short, from this side only, infinity square minus infinity is indeterminate plus 1 minus square root of x. So we need to find a means of simplifying this thing such that we won't have minus. We won't have minus again, because this minus is causing an indeterminate form. So how can we do this? And how can we remove the minus here? The best way to remove the minus here is to multiply the numerator and the denominator by the same thing here, but this will only turn to plus, because when this turns to plus, it will like have effect on this, and both together would give something positive. I don't know if you are getting the picture, but don't worry, when we start working on it now, you understand better. So the limit as x approaches infinity of square root of x squared minus x plus 1 minus square root of x over square root of x squared minus x plus 1 plus square root of x, then plus will also be here, square root of x squared minus x plus 1, then plus square root of x. This is a balanced expression, because when this cancels this, then we arrive at the initial question. So don't be confused that how did square root of ln x came in. And so people used to ask this question also, that when we want to rationalize, it should be the conjugate of the denominator and not the conjugate of the numerator. The idea in this in mathematics is that you should know how to twist what you have to get what you do not have. Just ensure that it is correct. That's it. I want to evaluate my integral problem. Integral of x raised by 5, x raised to the power of 5. Okay, don't let me use integration for now, because it looks, integration is a bit advanced. Let me use differentiation. Y is equal to x. Now I want to differentiate x now. I may decide to write it as y is equal to x raised to the power 3 over x squared. They are still the same thing, of course. They are still the same thing. So I may even decide to apply the quotient rule to this. Now let me apply the quotient rule. dy over dx is equal to v is x squared, du dx. When you differentiate the numerator, you arrive at 3x squared minus u, the numerator again, which is x cubed, dx. When you differentiate this, you arrive at 2x, then over, when you square this one, x raised to the power of 4. So when you modify everything, this is 3x squared times x squared. You arrive at x raised to 3x raised to the power of 4 minus 2x x cubed times 2x. Then you arrive at 2x raised to the power of 4 over x raised to the power of 4. Now 3x raised to the power of 4 minus 2x raised to the power of 4 is x raised to the power of 4. So x raised to the power of 4 over x raised to the power of 4 cancels out and give 1. And from the initial problem also, y equal to x, when you differentiate this, it gives 1. So knowing what to do, like trying to simplify or manipulate your question, just ensure that everything is correct. You can do it in any way, just ensure that it is correct. Now, rationalizing this one now, I may decide to rationalize with the numerator or the denominator, but this one did not even have a denominator that we can use to rationalize. But given a problem that we have over square root of something, we may decide to make use of the denominator as our factor of rationalization. So don't let it bother you that why do we introduce square root of this and square root of that. Now when you expand this, lim x approaches infinity. When you expand this, you multiply, this one will turn to difference of two squares, a minus b, a plus b. When you expand it, it will turn to a square minus b square, and this a, this part b. So when you expand it, it will turn to x square minus x plus 1, that is a square. Then minus b square, which is equal to x over square root of x square minus x plus 1 plus square root of x. So we can simplify the numerator here, minus x minus 2x. The limit as x approaches infinity of x minus x square. Okay, I want to simplify. I want to skip a step, but let me explain the step. I don't want to prolong this. X square minus 2x plus 1. When you simplify this, it will give you x square minus 2x plus 1. But you notice that it is the same thing as x minus 1 square. X minus 1 square over square root of x square minus x plus 1 plus square root of x. So with this, when x is equal to infinity, infinity minus 1 is infinity. When x is equal to infinity here, infinity minus infinity, this is still a problem. In everything we want to do, we should ensure that infinity minus infinity is out. Oh, somebody just tagged number 26. Okay, that will be the next problem after this. Please, you should send more questions if you still want us to continue. If there's still any question that you think that we need to discuss, just send them. So now we need to find a way of eliminating this minus. Think no further. You just need to express everything. When we're working with square root of x over square root of x plus maybe square root of y, they said that birds of same feather flock together. So because they all have square roots, when you want to divide through by a certain constant having a square root, it would penetrate into everything. What I'm saying is, in essence, is that look at this, square root of x plus square root of y over square root of z. When you want to divide everything through by square root of z, it would work easily. You just write square root of x over z plus square root of y over z, because they all have square roots. But look at a different case, square root of x plus square root of y over z. This case, you can't easily write square root of x over z because this one is not in the same category with them. Now, to make this z, to make the denominator to appear in the same category with them, what you need to do is to write it as square root of z square. Look at this, square root of x plus square root of y over this z, you write it as square root of z square. That's the trick. Now, this have a square root, this also has a square root sign. Now we want to make this one to have a square root sign. How should we do it? We need to put square root, then put square. It already has a square here, so we can put one more square to make it power of 4. So we write lim x approaches infinity. So this one will become square root of x minus 1 raised to the power of 4
over, when this simplifies, it gives 1 minus x minus 1 square again. So square root of x square minus x plus 1 plus square root of x. So with this, okay, let's even expand this. Let's expand this x minus 1 raised to the power of 4 to be sure of the output. Lim x approaches infinity. Square root of, when you expand this, x raised to the power of 4 minus 4 x raised to the power of 3 plus 6x square minus 4x plus 1. When you want to expand this, even without using your Pascaline triangle or your calculator, you know that we have, when we expand it to the power of 4, 14641. 14641. The signs will only change because we have minus here. At this point is plus, we just need to leave everything as positive over square root of x square minus x plus 1 then plus square root of x. Okay, let's open this on the new page. The limit as x approaches infinity of square root of x square root of x raised to 4 minus 4x raised to 3 plus 6x square minus 4x plus 1 3210 14641. Okay, that's right. Over x square minus x plus 1 square root of x square minus x plus 1, so plus square root of x. So now we can divide through by the highest power of the unknown and it would penetrate through the brackets, through the root. So let's divide through by square root of x raised to the power of 4. The goal is to eliminate the highest power of x. That's always the goal when we are taking the limit of a rational function as x is approaching infinity. Now let's do that. The limit as x approaches infinity of square root of, when the x raised to the power of 4 goes into the root, then we have x raised to the power of 4 over x raised to the power of 4 minus 4x raised to the power of 3 over x raised to the power of 4 plus 6x square over x raised to the power of 4 minus 4x over x raised to the power of 4 plus 1 over x raised to the power of 4 over everything over. When you divide this through by x raised to the power of 4 also, we have 1 over x square over x raised to the power of 4 minus x over x raised to the power of 4 plus 1 over x raised to the power of 4. So plus square root of this one also, x over x raised to the power of 4. Now when you take the limit, okay, let's simplify this. We need to simplify it before we take the limit. Limit as x approaches infinity. The numerator, we have 1 minus 4 over x, 1 minus 4 over x plus 6 over x square minus 4 over x raised to the power of 3 plus 1 over x raised to the power of 4 over square root of 1 over x square minus 1 over x raised to the power of 3 plus 1 over x raised to the power of 4 plus square root of 1 over x cube. Now when you directly take the limit as x approaches infinity, it is now easy to see that square root of, okay, this is 1, so let's put 1 down, minus 4 over infinity is 0, 4 over infinity is 0 plus 6 over infinity square is 0 minus 4 over infinity is 0 plus 1 over infinity is also 0 over 1 over infinity 0. So we have square root of 0 minus 0 plus 0 also plus 1 over infinity also square root of 0. And this gives, this is, let's assume that you are writing this at the back of a book or somewhere, because in limit, we don't usually write 1 over 0 equal to infinity. But it is something you can draw at the back of your book and observe that because you have 1 over 0, it means the answer is infinity. But in your workbook or in your exam sheet, don't write it there that 1 over 0 is equal to infinity. Just do it somewhere, maybe at the back of your book. So let's assume that this one is at the back of, because it is not right to put it in the answer sheet. So because of this observation, we have 1 over, because of this observation, we can conclude that 1 over 0 here is equivalent to infinity. The answer is infinity, not indeterminate. We only conclude that the answer, the conclusion is not even right to say that a function is indeterminate, that a limit is indeterminate, because that is when you would have to break the bond using some advanced trick like all these L'Hopital rules, sandwich theorem, summation and everything. So it is indeterminate is something we do with all those advanced methods. If not because the function is even indeterminate in the first, like some function like what we've done in the past, if not because they are indeterminate in the first case, we wouldn't have concluded that we resort to using L'Hopital rule, like the one we used L'Hopital rule for about 5 times that we solved by L'Hopital rule. So we wouldn't have concluded that the answer is equal to that. We would have concluded that the answer is equal to indeterminate, as it being that indeterminate is also a solution to some questions. Okay, the next question. This is number 33. Someone said 26. Question 26. Okay. Question number 26. Name. X approaches 0. X minus sin x over x cube. The first thing to do in this case is to check, as I've said before, that we should check if by direct substitution it will give 0 over 0. That's when we will know if we have to apply the rule. Okay, but it was because a teacher told me that 1 over infinity is no. 1 over infinity is not indeterminate. 1 over, and this, we are not even working with 1 over infinity here. 1 over infinity, 1 over 0 is what we got here. 1 over 0 by direct substitution, and we concluded that the answer is equal to infinity. But when you are talking about 1 over infinity is equal to 0. 1 over infinity, in limit, we believe that infinity is a technical way of writing, or can be technically written as 1 over 0. So 1 over infinity can be written as 1 divided by infinity, and we say infinity is equal to 1 over 0. 1 divided by 1 over 0. So when you cross multiply or when you transcript this, it will become 1 times 0 over 1, and this is equal to 0. So 1 over infinity is 0. I hope you get that. So let's continue with this. The limit as x approaches 0 of x minus sin x over x cube. So what we need to do in this case is to check by direct substitution firstly. So when x is equal to 0, we have 0 minus 0 over x is equal to 0. So because it gives 0 over 0, we can now apply the L'Hopital rule. So it gives lim x approaches 0 of, when you differentiate the numerator, this will give 1. Then when you differentiate sin x, it gives cos x over, when you differentiate x cube, it gives 3x squared. So 3x squared. Let's check again to see if we still need to apply the L'Hopital rule, or to know if we can conclude the answer from this expression. When x is equal to 0, cos 0 is equal to 1. The 1 minus 1 is 0 over 0 again. So we arrive at 0 over 0 again, and we need to apply the L'Hopital rule again. 1 over 0 was infinity. Was indeterminate? So from this place, we can differentiate again. Lim x approaches 0. When you differentiate this one is constant, it returns to 0. So when you differentiate minus cos x, it returns to sin x. When you differentiate cos, it returns to minus sin. But we already have minus here, so it returns to sin x over, when you differentiate the denominator here, it gives 6x. 2 times 3 is 6x. And we can write this as lim x approaching 0 of sine x over 6x. We can write this as, we can factor out 6 here. Then the limit as x approaches 0 of sine x over x, sine x over x. And that we've discussed, I told you that it's more like a famous identity, that the limit as x approaches 0 of sine x over x is equal to 1. So we can conclude that our answer is 1 over 6 times 1, which is equal to 1 over 6. But if you think that you want to know the reason why sine x over x is equal to 1, it is something you can prove using L'Hopital rule. It is even very simple to do. Just differentiate this sine x, it will give cos x. Then when you put x, when you substitute x with 0, then cos 0 gives 1. Okay, so the answer here is 1 over 6. Question number 25. We've solved 25 before. When we just started the lecture. We've solved it before. Let me see if I can still get it here for you. 25. Okay, I explained. Yeah, anyway, it is something I can quickly do again, because some people may just want to know how it works. 25 again. The limit as x approaches pi of 1 plus cos x over x minus pi square. So by direct substitution, cos pi is equal to minus 1. So 1 minus 1 is equal to 0. The numerator gives 0 over cos pi minus pi. Pi minus pi here also gives 0. 0 squared 0. So we apply the L'Hopital rule. When you differentiate the numerator, you get when you differentiate cos x, 1 plus cos x, you arrive at minus sine x over, when you differentiate the denominator here, 2 bracket x minus pi. So let's factor out the constants, minus 1 over 2. So we factor out minus 1 over 2 as follows. Minus 1 over 2 lim x approaches pi sine x over x minus pi. Let me write it again. Minus 1 over 2. The limit as x approaches pi of sine x over x minus pi. Now, when x is equal to pi, when x is equal to pi, sine pi is equal to 0, then pi minus pi is also equal to 0. So that's not all. It means we can still apply the L'Hopital rule again. So when you apply the rule, lim x approaches pi sine x approaches, as x approaches pi. So when you differentiate the sine x, you arrive at cos x over 1. And this is equal to minus 1 over 2. Cos pi is equal to minus 1. So minus 1 over 2 times minus 1 gives 1 over 2. And that's the conclusion. The answer is equal to 1 over 2. I hope you understand the solution step. Okay, is there any other question before, or we should just brief through the others? Yeah, it is not very clear. If there's any other question, you can just comment it before we move on, or we should just move on. Seems like this is quite dark. Okay. All right. Examine and define the domain of continuity of the following function. F of x equal to number 31. Somebody said number 31. Number 31. Okay, I'll just quickly brief through the number 31. I believe that is something you will understand. It is something you should understand based on this, based on the previous examples. Now, question number 31 is the limit as x approaches 0 of 1 over x squared minus 1 over 1 minus cos x. When you substitute x Yes, the video will be available after the stream. You can find it on the channel. So when x is equal to 0, 1 over 0 square, you arrive at infinity. We're working with limit now. 1 over 0, it is not that you won't put it in your workbook that 1 over 0 is equal to infinity. When I work that 1 over 0 is equal to equal to infinity. But it's something you note somewhere that when you are working with limit and you arrive at 1 over 0, then it is technically equal to infinity. So 1 over 0 here will give us infinity. Infinity minus, because 0 here is also equal to 1. So 1 minus 1 is also equal to 0. 1 over 0 will also give infinity. And as discussed before, that infinity minus infinity is undefined. So, but a better way to do this is just to convert these two fractions to a single fraction. When we convert this to a single fraction, it will be something that you'll be able to, when we are working with just one fraction, that's when you'll be able to apply your L'Hopital rule effectively. Now, let's convert this to a single fraction. The limit as x approaches 0 of 1 minus cos x minus x squared over x into bracket 1 minus cos x. So when you substitute x with 0 here, cos 0 is 1, 1 minus 1 is 0, this one is 0. 0 over 1 x equals to 0, 0. So this is a form that will take in L'Hopital rule. So let's apply the rule. The x approaches 0. When you differentiate this one, it is 0. When you differentiate cos x, it will give you minus sin x, but minus is here, so it will give you sin x. Minus, when you differentiate this x squared, it gives 2x. Okay. Yes, we have other methods for solving limit problems. We have sandwich theorem. Sandwich theorem is just like relating between two other parameters to get what you want. For example, if you want to evaluate the limit of sin x over x as x approaches infinity, as x approaches 0. So there's this trick that you will first draw a triangle. You will draw a very big triangle. Then you put the appropriate sides. Again, you will assume that this is a point from the center of a circle. Then you assume that this is a radius and this another radius. Then it forms a. This triangle is not well written. It's not well drawn. It should be something that would form, that would join well. So what I'm trying to say in essence is that it will form another sector here, apart from the triangle that was written initially. Then you will assume that there's another triangle again inside this sector. Now it is obvious that the first triangle, if the first triangle is T1, then the area of the triangle, because the sector is inside the triangle, so the area of the triangle is greater than the area of the sector. And the area of the sector is also greater than the area of the smallest triangle that is inside both the triangle and the sector. So this one is also greater than T2. So with this idea and with all the parameters you put, sin x, cos x, and with everything, when you simplify it, you'll be able to show that between both of them, just like getting 0 is greater or equal to 0 is greater or equal to x is greater or equal to 0. So from here we draw is or greater or equal to 0. From here it is obvious that there's no value between 0 and 0. So the only value between 0 and 0, since it is greater or equal to. But now we know that it is not greater than, because if it is greater than, then if it is less than, then there's no way to be greater than 0 here. And we draw the conclusion that x is equal to 0 based on this or equal to. So this is the assumption they make in sandwich theorem. Forgetting the other name they call it. So another method that we always use is series method. You resolve the problem into series using all these geometric series. Please, I need to change my direction. We resolve into geometric series like shit. Come with this. Can you see anything now? Okay. I think it's better now. So we use geometric series like the sum of x raised power of n from n equals to 1 to infinity. We use it to convert any function to this form. So from here, we'll be able to perform some tricky substitution, and we use expansion method also. Series, okay, we use infinite series, like the series of sin x. When you want to take the limit as x approaches 0, but this is even a direct function that is continuous at hypothesis equal to 0. But when you want to take the limit, assuming you want to take the limit of a complex function like sin x over x, a perfect example, and you write down the sum for sine, the series for sine, summation minus 1 raised power 2n plus 1 x raised to the power of n over 2n plus 1 factorial. So when you put in this and you divide also by x, when you expand everything, like you get x plus x raised power 3 over 3 factorial plus x raised power 5 over 5 factorial and everything over x. The first term we cancel out, and the remaining terms we give 0, 0, 0. So because x over x gives 1, then we have 1 plus 0, 0, 0 for the rest. So this one will be our answer. So that's another method we can use to break the bond. Now back to the one we're discussing. Sin x, when you differentiate the numerator, you arrive at sin x minus 2x. And when you differentiate the denominator, let's assume that we've expanded this. We have x minus x cos x. Let me write it somewhere so that we won't be confused. X minus x cos x. So when you differentiate this first one, you will get 1. And when you differentiate this remaining 2, let's put minus first, then open the bracket. So u dv dx, that is minus x sin x plus v du dx cos x. So from here, let's expand, let's modify it. X approaches 0, sin x minus 2x, 1 plus x sin x minus cos x. Okay, now let's check by substituting x with 0 to see if it will produce a good image, or maybe we still need to perform any other trick. When x is equal to 0, sin 0 gives 0, 0 minus 0. When x is equal to 0, 0 sin 0 is 0. Then 1 minus cos 0 is 1, 1 minus 1 0, still 0 over 0. So we need to apply the L'Hopital rule again. Lim x approaches 0. When you differentiate sin x, you call it cos x. Minus, when you differentiate this, minus 2 over, when you differentiate this, the constant will disappear. When you differentiate this, the constant will disappear, then x sin x will be differentiated. When differentiated gives x, what's happening to the constraint? Gives x cos x plus sin x. And when you differentiate this minus cos x also, it gives plus sin x. And it can be modified as the limit as x approaches 0 of cos x minus 2 over, so x cos x, because sin x and sin x are the same, so it will give plus 2 sin x. Now when x is equal to 0, let's substitute the value of x to know if you still need to apply the L'Hopital rule again or not. At x is equal to 0, we have minus 2. The numerator gives minus 2. Let's write it somewhere. Minus 2 over, when x is equal to 0 also, the denominator 0 times cos x 0. Then this sin 0 gives 0. 2 times 0, 0. Then the denominator gives 0. So it means we have minus 2. It means we have minus 2 over 0 technically. And we know that, any number 1 over 0 raised to power 1 over 0 is technically equal to infinity. So minus 2 times infinity, minus 2 times 1 over 0, which we assume to be equal to infinity in limit. Minus 2 times infinity is equal to minus infinity. So our answer is equal to minus infinity. You just need to understand this step. If you understand the step and you understand the identities and you understand how it works, you won't have problem with solving any problem of this kind. Okay, I think there's no more question on limits. Okay, continuity. For continuity, there are some ideas that we put together. Okay. Examine and define the domain of continuity of the following functions. This is exponential infinity 0. E raised to power infinity is equal to infinity because e is greater than 1. The rule is that any number, okay, you know that e itself is a number. Trigonometric identities. Well, it is advisable that you study different trigonometric identities before you start dealing with problems like, yes, especially for integration, you need to master the trigonometric identities. You need to master it because it is very useful, especially these trigonometric identities. You really need to master it. So when you're talking about a raised to power of infinity, if you like, you call it e raised to power of infinity. We know that e itself is a number. It's a number that was modified with a name that we call, with a letter that we call e. Just like pi. Pi is also a number, of course. Although we do not know the exact value of these e and pi. We only have approximate answers for them. So a raised to power of infinity. The rule is that if a is greater than 0, the answer is equal to infinity. For example, numbers greater than 0 like 1, 2, 3, even 3.5, 3.4. A quick test. We said that any number greater than 0, when we raise it to the power of infinity, then the answer is equal to infinity. May I ask you this? What is pi raised to the power of infinity? Pi raised to the power of infinity. Just type your message. I will see it in the comment section. Pi raised to the power of infinity.
Okay, thank you.
Okay. While you do that, let me just put down this. A raised to infinity. A raised to infinity. When a is less than 0 gives 0. So pi raised to the power of infinity is infinity. Yes, that's correct. And that's because pi is greater than 0. No, pi is between 3 and 4. That's why we have 3.141. It has moved away from 3 a little. So it is even not something very small, like just 1. Now we can even still think that, because even, okay, let me throw this question again. What is 1.000001 raised to the power of infinity? 1 raised to the power of 1.000001 raised to the power of infinity. Okay, to limit it up, let me just say the answer is infinity. That's because no matter the little percentage of which the number is greater than 0, as far as it is still greater than 0, it is still equal to infinity. Another example again, 0.000000, no matter the number of 1, because of this small one, it is still greater than, this number is still greater than 0, but with a very little percentage. So we say that this number is greater than 0, and because it is greater than 0, this number raised to the power of infinity is also equal to infinity. Okay, let me just leave that for now. I said a raised to the power of infinity is equal to infinity if and only if a is greater than 0, and it is equal to 0 if a is less than 0. Do you know something? One thing I enjoy in mathematics is that with a little fact, with just one small idea, you can expand it to get some other ideas. Like this now, I said that If a is greater than infinity, if a is greater than 0, then a raised to the power of infinity is equal to 0. Now we want to know if we want to know the answer. We want to know the answer when a is less than 0. Now you can just say a, since a is less than 0, let's say it is 1 over a. 1 over a raised to the power of sorry, there's a little mistake here. Shouldn't be a is less than 0. For a is lesser than 0 also, it is still equal to infinity. For a is greater than 0 or a is less than 0, you know, when a is less than 0, it is minus something, maybe minus a or minus 1, minus 2, minus 3. So minus something raised to the power of infinity is still infinity because of this 3. So that's not what I wanted to bring actually. What I was trying to say is that for all values between 0 and 1, between 0 and 1, between 0 and 1, when they are raised to the power of infinity, the answer is equal to 0. Okay. Is this thing clear like this? Sorry. For all values between 0 and 1, if a is greater than 0 but a is less than 1, then you know that a is between 0 and 1. So for all values between 0 and 1, the number raised to the power of infinity is equal to 0. We can prove this, that you know that values between 0 and 1, they are numbers like 1 over 2, 1 over 3, 1 over 4. They are numbers that can be expressed as fraction. And when they are expressed as fraction, the denominator is usually greater than the numerator. The denominator is usually greater than the numerator. So in this case, we know that a is also a number that the denominator is greater than the numerator. And they are the numbers between 0 and 1. So I don't know, maybe I should use a number to explain, because if I use this, you may not understand the way I will draft it. Let me just use a number. 2 over 3 raised to the power of infinity. This can be written as 3 over 2, you know, because we change it as 3 over 2, minus will come to the power, rule of indices. So minus will come here, then minus infinity. Now we can now write this as 1 over, because of this minus, rule of indices again, 1 over 3 over 2 raised to the power of infinity. And you know, we've said it before that any number greater than 0 when raised to the power of infinity is equal to infinity. Now this is the number. 3 over 2 is the number. It is greater than 1. It is greater than 1. Yes, it's greater than 1. And when it is raised to the power of infinity, it is equal to infinity. It is equal to infinity. So we now arrive at 1 over infinity, which is equal to 0. So what I'm saying in essence is that 1 over any number a raised to the power of infinity, we can divide it into 3 parts. Any number raised to the power of infinity is equal to infinity if a is greater than 1. If a is greater than 1, and equal to 0 if 0 is greater than a is greater than 1. This is just a technical way of saying that if a is a number between 0 and 1. Okay, for the third, when a is equal to 1, this is indeterminate. Because when a is equal to 1, we have 1 raised to the power of infinity, and when we try to modify this, we have e raised to the power of infinity then 1. Then 1 is 0. Then 0 times infinity is not a number that has conclusion. So let's call it indeterminate. So the answer I was attending to, the question was, okay, the person asked that, please, is exponential infinity 0? Exponential infinity. Okay, now because the exponential number, is greater than 1, E itself, just like pi is equal to 3.142, E is also equal to 2.7182, and we say that it is greater than 0. It is greater than 1. Because it is greater than 1, we conclude that the answer is infinity. So e raised by infinity is equal to infinity. Just understand it. Okay, let's quickly check the domain of continuity of the following function. Okay, in a layman word, I would say that the domain of continuity, the range of values, are the range of values for which it is defined, for which the function is defined. Range of values for which the function is defined. For example, f of x is equal to 2x plus 3 cube root of x. The domain is the range that x can take. For example, x can take the negative numbers. Cube root of negative numbers is possible. Taking the cube root of negative numbers is possible. For example, cube root of -8 is equal to -2. Because -2 times -2 times -2 in 3 times will give us -8. So it is possible. So because it is possible for both negative and positive, and this is also possible for both negative and positive, and if, in short, for all numbers, for all real numbers, this is possible. So we say that the domain of this function, the domain is x. They call it x is a member of R. X is a member of R. It means that x can take all real numbers. Real numbers are numbers that can be expressed. Numbers, we have 2 types of numbers basically. 2 types of numbers. The first one is the real number, and the second one is the complex number. The complex numbers are the numbers that, like square root of negative numbers, square root of negative real numbers, like square root of -4, it is equal to 2i. 2i, because of this I, we call it a complex number. So when you're even working with the domain, you don't have anything to do with complex numbers. We don't have anything to do with complex numbers. So because this is true, x can take all real numbers. We say x is a member of real numbers, all real numbers. X is a member of real number. Assuming there's a range of value, or there are some values that x can take, then we would write except 2. No, we get there also. We see some examples. Now the second one here, the second example here, that is f of x equal to 1 plus x cube. F of x is equal to 1 over 1 plus x plus 3. X plus 3. Now, by observing this, we know that rational functions always have problems. Rational functions, even in integration also, our problems are usually with rational functions. In limit, the limit we just finished discussing. Even the L'Hopital rule we say we'll be using, it is something that we use for rational functions, because rational functions always give like 1 over 0 or infinity over infinity or 0 over 0. So because of these complexities, we need to pay more attention to them. Now we have a rational function here, and we know that for this to be true, actually for this, x can take all numbers. When x is equal to 1, x is equal to 2, x is equal to 3, we have real numbers. When x is even equal to -1, -2, -4, -5, -7, when x is even decimals like 0.1, 0.3, you always get real values for this. The number you always get will be number that can be found on the number line. Number that can be found on the number line. Now 1 over x plus 3. The only problem we have here is that at the point where the denominator is equal to 0, at the point where the denominator is equal to 0, we need to calculate the point, so that when the denominator is equal to 0, we know that at that point 1 over 0 is not a real number. So that is the point we need to exclude from our solution set. Now, to get the point where the denominator is equal to 0, we'll be the one to equate the denominator to 0. We have to eliminate the denominator to 0. So we write 1 we write x plus 3 is equal to 0. So when x plus 3 is equal to 0 and you make x the subject of formula, you solve for x, you see that x is equal to minus 3. So at the point where x is equal to minus 3, 1 over minus 3 plus 3 is equal to 1 over 0. So because 1 over 0 is not a number, it is undefined. We are not working with limit again. So when you see 1 over 0 in just normal calculation, like you are trying to simplify an expression, it is undefined. So 1 over 0 is not a number. So we can say that x can take all numbers, all real numbers, as I've mentioned before, that x can take all real numbers. But now we've discovered that minus 3 should be excluded from the set. So we can conclude that x is a member of all real numbers. X can take all real numbers except, then you draw the set, except minus 3. And this is the answer. X can take all real numbers except minus 3. That's what this means. X can take all real numbers except minus 3. Another example here, 1 over x squared plus 1. 1 over x squared plus 1. 1 over x squared plus 1. F of x. So this is just like the first one. We call it a rational function. Now we need to check. We see that x can also take all numbers here, but we need to check the point at which x squared plus 1 is equal to 0, so that we can know where the value of x that we make the denominator equal to 0. So when we equate the denominator to 0, x squared plus 1 is equal to 0, we see that x squared is equal to minus 1. So x is equal to square root of minus 1. This is a complex number, like square root of a negative number. So because this is a complex number, we can't remove this from the set, because we are always working with real number sets when we are working with all this continuity, domain, range. So this is not even a real number, so we don't need to pay attention to it. We can just conclude that x is a member of R. That's the only answer. X can take all real numbers, all the real numbers, because the one that should have been the one that we should have excluded now happens to be a complex number. So it means that we don't even have anything to do with it. Let's have to conclude that x is a member of R. A similar example, this one would be from the workbook. F of x is equal to 1 over x squared minus 1. F of x is equal to 1 over x squared minus 1. Okay, what we need to do here is to equate the denominator to 0. X squared minus 1 is equal to 0. Then we see that x squared is equal to 1, and x is equal to plus or minus 1. So x is equal to plus or minus 1. It means that at the point where x is either plus 1 or minus 1, then it will give 1 over 0. When you substitute x with plus 1, 1 square minus 1 will give you 0. Then 1 over 0. When you substitute x with minus 1 square, that is 1. 1 minus 1, 0. So we see that 1 over 0 and 1 over 0 will only occur at plus or minus 1. So we can conclude that the answer to this is it will be undefined. So because of this is our answer. X is a member of R except minus 1 and 1. So that's just how to go about all the questions under this topic. You just check for the values at which it is not undefined. So this also happens. Okay, in some cases you may be told to calculate if the function is either continuous, whether it is continuous or discontinuous at one point or the other. Okay, let's talk about this first. X is a member of R, but x is not equal to minus 1 and 1. Now look, there's something. You may be told to calculate the points of discontinuity. This is the point for which the function is continuous. This is the point, x is a member of R, that for all real numbers except this one, the function is continuous. Now, to check the values for which the function is discontinuous, these values at which it gives 1/0 are the points at which it is discontinuous. So we say that for continuity, we have x is a member of R except -1 and 1. So for discontinuity, note that they are the opposite of each other. This is true for all real numbers except these points. So for discontinuity, then it is just this set -1 and 1. That's the like these are the points at which the function is discontinuous. Okay, the example I said I wanted to give. Look at this function, x plus 1 over x minus 2. Now the question is that, is this function continuous at the point x equal to -1? Or they may say that, discuss the continuity of this function at the point x equal to -1. So what the question is asking indirectly is that we should check maybe the function is continuous at the point x equal to -1. So when you substitute -1 here, -1 plus 1 is equal to 0 over -1 minus 3, -1 minus 2 is equal to -3, and this gives 0. So because this is a real number, it is a subset of R, it means that the function is continuous at that point. The function is continuous at that point. Okay, what if we are told to calculate the point at which it is discontinuous? To get the point at which it is discontinuous, just equate the denominator to 0. It is something we discussed before. So when you set the denominator as 0, you calculate the point at which it gives an undefined expression. So at the point x equal to 2, we see that 2 minus 2 is equal to 0, and the numerator gives 3 over 0, and this is undefined. So at the point x equal to 2, it is undefined. It is discontinuous. Rather, we don't make use of this undefined here because we're working with continuity and discontinuity. It is discontinuous. So it is continuous for all x is a member of R. The function, this is the only point at which it is discontinuous. Then it is continuous for all x is a member of real numbers except that point that it is discontinuous. That's it. Okay, there's a question here. F of x from the workbook. F of x is equal to x squared plus 1 over x squared plus 1 over x squared. So we want to check whether this is continuous or discontinuous at some certain points. Now, because this term does not have a fraction, this one is independent. X can take all real numbers, all numbers, -1, -2, -3, -10, minus 0 points, and any other number. But look at this one, because this is a rational function, 1 over x squared. So we know that surely the denominator at a certain point should give something that is discontinuous. Now equate the denominator to 0 to get the point at which it is discontinuous. X squared is equal to 0 implies that x is equal to 0. Now at the point where x is equal to 0, although this one will give us 0, but this one will give us 1 over 0, which is undefined. So we can conclude that the function is continuous. Okay, let me use C for continuous and D for discontinuous. The function is continuous at the point x is a member of all real numbers. The function is continuous for all x is a member of real numbers except the point where x gives 0. And it is discontinuous. They are opposite of each other. This one is saying that all real number except 0. Then this one will be saying that at that point 0, where the function is discontinuous, at that point 0 where it was excluded. That is the main point where the discontinuity will take. Okay, you can just look at it and select any other questions that you think that we need to discuss. That number 5 is a little bit tactical and it will need some. Okay, maybe we should do number 5. Maybe we should do number 5 together. So number 5 needs some extraneous idea. F of x is equal to square root of x plus 1 over x minus 1. So we need to split this square root of x plus 1 over square root of x minus 1. We need to put into consideration two things into consideration. One is that a function is discontinuous at the point where it gives a number 1, 2, 3, 4, 5, 6, any number over 0. The second is that it is discontinuous at the point where it gives a complex solution like square root of minus 1. What I'm saying in essence is that when you have 1 over square root of x, so to check you have to put two things into consideration here. The first is that the point where the denominator will give you negative numbers, like 1 over square root of minus 1, square root of minus 2, square root of minus 3, square root of minus 4. They are all at those points. The function is discontinuous because square root of a negative number will only give you the square root of the real part and I, and that I is complex number. So we don't make use of complex number when we are working with continuity and discontinuity. So at the point where x is, for all values of x lesser or equal to 0. Okay, let's even consider two cases. For all values of x lesser than 0, then the function is discontinuous. Values that are lesser than 0 are minus 1, minus 2, minus 3. And for those negative numbers, the function is discontinuous. Also, for the value of x at which the denominator is equal to 0, this function is also discontinuous. When the denominator is equal to 0, square root of x is equal to 0, then x is equal to 0. So this one will also give us 1 over 0. Then the function is discontinuous at that point also. But we can combine this together. X is less than 0 and x is equal to 0. The point of discontinuity, we can say x is lesser or equal to 0. So at the point where x is lesser or equal to 0, the function is discontinuous. So if you want to calculate the point for which it is discontinuous, it will just be the other way around, that for all x is greater than 0. If x is not lesser or equal to 0, then the opposite would be x is greater than 0. So these are the points for discontinuity for this function, for this 1 over square root of x. Now, the reason why I made mention of this is for you to understand that for this type of question, we need to consider two cases. We need to consider two cases. And this one is a little bit technical because we need to consider the cases for which the numerator will give 0 and the denominator will also give 0 at the same time. Apart from the case that the denominator gave 0 at some certain points, then you also need to consider the case at which it won't give you square root of negative numbers. Okay, look at this. Square root of x plus 1. Okay. The solution set for square root of x plus 1. For this one to be real, we know that x plus 1 must be greater than 0. For the solution to be real, we know that the value of x plus 1 must be greater than 0. Because if x plus 1 is less than 0, so if x is less than 0, then it will give you square root of a negative number like square root of minus 1, minus 2, minus 3. So we say that x plus 1 must be greater than 0 if the function should be continuous. Then x plus 1 must be greater than 0. That's for the numerator. For the denominator, x minus 1 must also be greater than 0. So these are the simultaneous points at which both would yield a real number. But for this one, we can see further peek into x, and we discover that x is greater than minus 1. And for this part also, x is greater than 1. X is greater than 1. So when you what is it? It won't be very clear. Okay, let's see if it will be clear. It's assisting with this. Sorry, some minutes. Yeah, let's go. To change the location. Thank you. So at the point x is greater than minus 1, the function is continuous. And at the point where x is greater than 1, the function is also continuous. But you will notice that between both points, there's an intersection between them. And at that point of intersection, something would be wrong here. Now, for the first one, x is greater than 1. For the second one, x is greater than, for the first one, x is greater than minus 1. And for the second one, x is greater than 1. Now, this one, for x is greater than 1, the point of intersection between them, let me just put this symbol. The point of intersection between them is the point where from minus 1 up to 1, that's the point of intersection between them. This should be a curved bracket because it is a closed set. So this is the point of intersection between them. So at that point of intersection, you will notice that one will be positive and the other will be negative. One will be positive and the other will be negative. Okay, let us first express this function in this form. F of x is equal to square root of x plus 1 over x minus 1. So in this form, you see that, okay, let's just pick an example from this set. Let's pick an example like x is equal to minus 1 over 2. You know, minus 1 over 2 is between minus 1 and 1. So, and even if you like, you can pick 0. Well, let's even pick 0. So when you substitute 0, 0 plus 1 will give you 1 over 0 minus 1. And this will give you square root of minus 1. So at this point, it is discontinuous because it does not produce a real number. So it means that at the point of intersection between these two, between the numerator and the denominator, it is discontinuous. Okay. Now let's look at the values for which this one, the values at the back. I'm talking about the values at the back. I said the values at the back. What I meant by that is that the values, the opposite side of this curve. You know, for this one, we concluded that x is greater than 1. Now let's look at the values for which the values such as x is the range for which x is lesser than 1. Pick a set, pick a number, say minus 5. So minus 5 plus 1, that is minus 4. Minus 5 minus 1, minus 6. So minus will cancel out to give a positive number. Let's do it again. Square root of, when x is equal to minus 5, minus 5 plus 1 will give you minus 4 over minus 5 minus 1, that is minus 6. So this will cancel out. So the idea is that we pick the points of intersection, and we also pick the point that x on the numerator and the denominator will both give 0, will both give negative numbers. Like x plus 1, when you substitute the value of x, it will give a negative number. And when you substitute it into the denominator also, it will give you negative number. So that's the solution for the continuity, yes. So for this continuity, we've concluded already that the point between minus 1 and 1, the point between minus 1 up to 1, That's the point for which it will be discontinuous. So for the points for which it will be discontinuous, we just say x is a member of R. When you get just one of the answer, maybe discontinuous or continuous, you'll be able to get the other easily by just saying the first one, except x is a member of R except the second one or the first one, -1 and 1. And that's the answer to this question. If you have any other, you can just point at it so that we can work it out together. Just comment it. Okay, let's just do number 6. F of x is equal to 3 over x squared minus x. X squared minus x. So we can write this as 3 over x into bracket x minus 1. So we know that to get the point of discontinuity, the denominator must be equal to 0. The point of discontinuity, the denominator must be equal to 0. So x into bracket x minus 1 is equal to 0. We want to calculate the values of x that will make this function undefined, something over 0. This is 3 already, 3 over 0. So when you solve this quadratic equation, x is equal to 0 or 1. So it means that when you put x equal to 0, then it will give you 3 over 0. And when you put x equal to 1, it will give you 3 over 0. So at this point, the function is discontinuous. So for the function to be discontinuous, we say x, we just pick from this set 0 or 1. So maybe in the exam, something like this might come out and they say that at which of these points is this function discontinuous, and you just see maybe ordinary 0 like this, ordinary 1, another option, ordinary 1, then another option again, 0 and 1 together. If you pick this one, the answer won't be correct. If you pick this also, the answer won't be correct. But this is the expected. Most of us, we used to hurry up that we just look at it and just quickly conclude that time is going, let me pick this one, Jerry. I've seen one of them, let me quickly pick it. And you won't even consider the fact that there's one that is better than the one you picked. Okay. That's the answer for that's the discontinuous points of the function. To get the points for which it is continuous, it is always easier when I said it earlier that it is always easier when you already have 1 point. So for this one, x is a member of R, real numbers, except 0 and 1, except the one we got for the first. So that's cheaply the answer to the question. Number 7. Number 7 is also one in this form. Just equate the denominator to 0. Number 7, when you equate the denominator to 0, you have x is equal to plus or minus 2. And at the point x equal to plus or minus 2, that's the point of discontinuity. So the function is discontinuous at the point x at the point minus 2 and 2. And it is continuous at the point x is a member of R except minus 2 and 2. Someone said number 13. Oh, there's still more here. I need to straighten it up. Number 13. Oh, number 13 is a piecewise function. They call it piecewise function. There are functions that you will be given some ideas, some hints on how to, but you'll be given some ideas on the values that can take and the values it can take. So you'll be expected. The expectation is that you should calculate the discontinuous points from what you already have. So f of x, is there even need to put anything to put pen to book for this one? So something you can just look and inspect what the answer is. Number 13, For f of x is equal to minus x if x is less than 0, and x squared if x is greater than 0. Now, we want to calculate the point. We know that for this point, for this given range, for all values of x less than 0, the function is continuous. For all values of x greater than 0, the function is also continuous because it produces a real number. So these are the points for which it is continuous. But for the points that it is discontinuous, they won't give you information about the points. Now, we have this information that when x is lesser than 0, the function is equal to minus x, and when x is greater than 0, it is equal to x squared. So the point at which it is discontinuous is the point where they do not give us anything. That is the point where x is equal to 0. They told us that at the point where x is less than 0, it is continuous. At the point where x is greater than 0, it is continuous. But they did not tell us anything about the point where x is equal to 0. So the point at which it is discontinuous is easily the point at which x is equal to 0. Okay, so I should put a title. Number 13, f of x minus x squared. If x is less than 0 and x is greater than 0. So we have the value at which x is less than 0, the value at which x is greater than 0. But what of the value for which x is equal to 0? So because it did not give us anything about the point at which x is equal to 0, the function is discontinuous at the point where x is equal to 0. And it is continuous. I told you when you have one, it will be always easier. It will be easier to get the first. Now, you can just conclude that it is continuous for x is lesser than 0 and x is greater than 0. Or you should conclude that it is continuous for x is a member of R except 0. In each of the cases, what you are still saying is that the point at which x is equal to 0 is the only point for which it is discontinuous. Okay, let's look at another one again. Number 13. We've solved number 13. So number 14. Just look at number 14 and conclude. Just send the answer just send it as comments. Number 14. What's the value of x for which the function is discontinuous? For number 14, the value of x for which the function is discontinuous. For number 14, the function is discontinuous at point so. Just put it down. Okay. While I await some comments, number 15. F of x is equal to x plus 1 over x squared minus 6. X squared minus 6. So, to solve this, we need to consider the point at which the denominator is equal to 0. This is a mistake actually. This x base x squared is a mistake, so just ignore that. X plus 1 over x squared minus 6. So the point at which the denominator is equal to 0, that is x squared minus 6 equal to 0. Then x is equal to plus or minus square root of 6. So the point of discontinuity is the point where the denominator is equal to 0, minus 6, square root of minus 6, and square root of 6. Thank you. I've seen a comment on number. Wait, the comment is forwarded by Clever Love, number 14. No, that shouldn't be right for number 14. For number 14, it is discontinuous at the point where x is equal to 0, because no information is given about the point where x is equal to 0. We only have the information that when x is less than 0, then we make use of this one. When x is greater than 0, we make use of this one. But what about the point where x is equal to 0? So no information is given about the point. So it means the function is discontinuous at the point x equal to 0. Now let me just give you this function. X f of x is equal to x square if x is greater than 10 and minus x square if x is less than 10. Can you tell me the point at which this one is discontinuous? This function, this piecewise function, tell me the point at which it is discontinuous. F of x is equal to x square if x is greater than 10, then minus x square if x is less than 10. Then the point at which it is discontinuous is yes, that's correct by test, the point at which x is equal to 10, because there's no information given about the point where x is equal to 10. So that's the point for which it is discontinuous. The same applies for question number 14, because we are not given the point at which x is equal to 0. It is discontinuous at the point where x is equal to 0. Number 15, x plus 1 over x squared minus 6. So we've solved that already. Now you equate the denominator to 0. Yes, clever love. The answer is correct. So minus 6 and 6 is the answer to number 15, because at the point where x is equal to minus 6, when you square it to give you 6, and 6 minus 6 gives 0. So 1 over 0. And the point at which it is continuous is the point at which is, you say x is a member of R except minus square root of 6 and square root of 6. So that's just all about this continuity and discontinuity for this level. Number 11. You need to do some little algebra. Number 11 before you get the answer. Number 11. F of x is equal to 1 over x minus absolute value of x. The method remains the same, that we calculate the point at which the denominator is equal to 0. The denominator, x minus absolute value of x, is equal to 0. That's the first step. We equate it to 0 to get the values at which it gives 0. Okay, now we need to solve this. X, we know that this absolute value of x means that x will be positive or negative. But we notice that when x is positive, it will cancel out, and it will just be like cancelling out what we wanted to solve for. So it means we can't make use of the positive, we can only make use of the negative. So we can write x minus x. In essence, absolute value of x is equal to plus or minus x. But because the plus will cancel out if you should consider it as a different case, so I only wrote the minus, the negative part. And when we equate it to 0, we arrive at 2x is equal to 0. Equating it to 0, it means we are solving for the barrier. Now we know that for the point where the denominator is greater than 0, the function is continuous. At the point where the denominator is greater than 0, the function is continuous. Or the point where the denominator is less than 0, it means it is continuous. But the point where the denominator is equal to 0 is the point for which it is discontinuous. That's why I equated the denominator to 0 here. So when you perform all necessary simplification, x minus x, you arrive at 2x is equal to 0. And that's not even all. If we should inspect this function, we say that for all positive x, I cancelled out the positive part of for plus or minus x, I cancelled out the positive part. That's because for all positive parts, for all positive numbers, this one, the denominator will always give 0. When x is equal to 0, 0 minus 0 is 0. When x is equal to 1, 1 minus 1 will be equal to 0. When x is equal to 2, 2 minus 2 will be equal to 0. When x is equal to 3, 3 minus 3 will be equal to 0. And everything and it continues in that form. So we can conclude that at the point where x is greater or equal to 0, When x is equal to 0, 0 minus 0 is still equal to 0. For the point where x is greater than 0, then the function is discontinuous because it will give 1 over 0. When x is not greater than 0, I mean when x is less than 0, like minus 1, minus 1 is lesser than 0. So when x is equal to minus 1 minus, absolute value of minus 1 will be 1. Minus 1. This is just an example out of the infinite values, minus 2. So I'm just trying to show that for the opposite side, it will be continuous. When we be thinking that why should it be that only when x is greater when x is greater or equal to 0, but for the point where x is less than 0, then it is continuous. It is just a technical something, actually. It is not everything that we do by solving, by calculating. There are some that you do by inspection. I just look at it that no, at this point where x is positive, then this will cancel out and give 0. Okay, I think that's all about this. You can take number 16 as something you should do as practice. Trigonometric functions, equations, and inequalities. Trigonometric function, equations, and inequalities. Okay, let me just explain how to go about number 1. If sin x is equal to 1 over 3, if sin x is equal to 1 over 3, and the value of x should be between pi over 2 and pi. It is a different case that the value of x is between 0 and 90. And you know that we always make use of this right angle triangle to solve this type of problem. But in this case, we won't be making use of it because it will fail. We always make use of this when we are solving for x is lesser or equal to, for 0 is lesser than theta and theta is less than 90. That's why we always make use of this. If you notice, this is not either this or this. It's not up to 90 degrees. It's not up to 90 degrees. So it is still if you should make it 90 degrees, then it should cover everything here. And for this part also, when you extend this, then this is for this whole part, it will form angle 90 degrees. So because of the additional information we have here, that at the point where pi over 2 is lesser than x is lesser than pi, this is showing that the value should be between 90 and 180. And we know that this can never be between 90 and 180. So it means that this method will fail. We can't use this method. So we need to devise another method of solving it. But from the previous videos I've made so far on trigonometric, you should know that sin x, when equated to 1 over 3, by solving for both cases, the case at which sin x is actually equal to 1 over 3, we take that one as case 1. And another case, sin pi minus x is equal to 1 over 3. We call it case 2. You know that at this one, sin x is still the same thing as sin pi minus x, but we express it as sin pi minus x to increase the yield of the solution. And I explained maybe to some people, that when you have something like this, maybe sin x is equal to 1 over 2, and the sine function is like this. The sine function is parabolic. It has 2 points at each point on the graph. If sin x is equal to 1 over 2, sin x is equal to 1 over 2, it means that at the point 1 over 2, it has 2 points. This first point where it cuts is while going up, and the second point at which it cuts it while coming down. That's why we always have two answers that's why we always have two solution sets to each trigonometric equation. So in this case, sin x equals 1 over 2 is the first, and that's for this point. Sin pi minus x, pi already has the end point. Then we want to minus something so that we can get this point. Pi minus x is equal to 1 over 3. So by solving each, our 2 pi k will come in since the sine function is periodic. As this one form this parabolic movement on the positive axis, it will come down again and form another one up again. And this one will also continue and cut both points again. So it will cut the parabolic points infinitely. That's why we always introduce the 2 pi k in the equation. Sin x is equal to 1/3. It's the same thing as sin 2 pi k plus x, or you say x plus 2 pi k is equal to 1/3. When you take the sine inverse of both sides, sine inverse of 1/3, and you get the value of x is equal to 2 pi k minus 1/3. And one thing we should be mindful of, one thing we should put into consideration is that, wait, okay, I think the answer here needs to be modified. Shouldn't be this. When you take the sine inverse of both sides, 2 pi k plus x is equal to sine inverse of 1/3. And when you make x the subject of formula, since k can either be positive or negative, so it is still safe to write either positive or negative on the right hand side. So sine inverse of 1/3 plus 2 pi k, that's the solution to the first set. But we know that this one can never be a solution, because for this one, x at the point where k is equal to 0, when k is equal to 0, the result becomes sine inverse of 1/3. So this sine inverse of 1/3 is suggesting a point between 0 and 90. 0 and 90. And we know that we want to solve for the values between pi/2 and pi. So at this point, we can't use this. So let's use the second solution set. Pi minus x, we know that pi is equal to 180. Pi is equal to 180. So when we subtract something from it, it will reduce that 180 a little. So by reducing 180 a little, it will fall into this range, the range between pi/2 and pi. So we solve the second. Sin pi minus x equals 1/3. But we start by adding 2 pi k to it. Sin pi minus x plus 2 pi k. We equate it to 1/3. Then when you take the sine inverse, pi minus x. So sin pi minus x, pi minus x plus 2 pi k is equal to tan inverse of 1/3. So when you make x the subject of formula, pi minus tan inverse of x, tan inverse of 1/3 plus 2 pi k. So we know that this must surely be the solution set. So we need to calculate to get this perfectly. X must not be greater than 0, because when x is greater than 0, when k is greater than 0, like when k is equal to 1, 2 pi plus any number is actually greater than 2 pi. So it means k can't be equal to 0, but k can only be equal to 0, so that the value will fall between 90 and 180. So what I'm trying to summarize is that x is equal to pi minus tan inverse of 1/3 plus 0, and that is pi minus tan inverse of 3. Pi minus tan inverse of 1/3. That's the value of x. Now, our expression a is equal to 5 tan x plus 4 cos square x over 3 sin x. And we already have x as pi minus tan inverse of 1/3, so we just substitute it into this equation. A is equal to 5 tan x plus 4 cos square x over 3 sin x. Then a is equal to 5 tan x. Tan, our x is equal to, the tan I got is from, oh sorry, this should be sine. This should be sine. Sine inverse of 1/3. So it has been rectified. Should be sine. So the tan I'm working with now, someone said it is not clear. That's how I end. So when x is equal to pi minus sine inverse of 1/3, then pi minus sine inverse of 1/3. This one is not clear again. So plus 4 cos square pi minus sine inverse of 1/3 over 3. We already have sin x as 1/3 even from the question. So we put 1/3 there. And a is equal to, when we simplify this is because the period of tangent is pi. So we arrive at 5 tan minus, this minus will come out, or I say minus sine inverse of 1/3 plus, when you simplify this also, you get 4 cos square sine inverse of 1/3 over 1. Or the essence of all this is just to simplify. I can just say that just simplify the function to get the final answer. But you already have the expression already. What to say? Okay, please, is it clear now? If it is clear, if it is clear from your MP, let me just forward it. I'm trying as much as possible to make it visible to everybody. So people said that the video is not clear. Please, if you can see it clearly, please just forward it. Let me know about it. Okay, the sense is better now. All right. So with your calculator, you can just compute this. This is equivalent to minus 5 tan. This simplification is just unnecessary. It is something you can do with your calculator. I believe that most of you are using this Casio FX991 years. I want to finish the take-based question. That's a good idea, Sha. So cos square x is equal to 1 minus sine square x, and sine x will eliminate this, we have 1/9 equals to 1. Then when you simplify this, tan sine inverse of x, tan sine, and this is equal to x over 1 minus x square. I'm able to input it sine or tan, able to input it tan sine inverse of 1/3. Please, which part? Because I've rectified the only mistake here. Pi minus sine inverse of 1/3 has been rectified. The A I'm working with now. Okay. The A I'm working with now should be the A I'm working with now is from the question that A is equal to 5 tan x plus 4 cos square x over 3 sin x. Now I already have the value of x as pi minus sine inverse of 1/3, and I need to substitute it into the equation. So I want to substitute this value of x into this equation. It is something you can actually do with your calculator, and you get a defined answer. So 5 tan x will give you minus 5 over 2 so 2, and 4 cos square x will give 4 cos, let me to input it. That's what to give us. Should be about 8/9. 8/9 times 4, 36/9. 4 times 8, 32/9. So this is what the final expression gives, and this is the answer. Yes, this is the answer. Just understand the where they are trying to put the question that they know that a lot of people would want to use the value between 0 and 90. And if you try to solve this using this triangle stuff, this right angle triangle, you will see that it will give you a wrong answer and a correct answer. So you need to understand how and the trick on how to go about your question. So you can check if you still want to master how to solve equations like sine x is equal to 1/3. You can just check the YouTube. You can check the video posted. It was posted about 2 months ago. So that was, or maybe you can just message me. I'll forward it to you. I'll forward it to you. So that's all about the question number one. I wish we can do more, but my phone is not very low. Okay, I think we can end the live stream now because of time. If there's still enough time, we can still do more at night, maybe in the group or not here again, but in the group. So I believe that the little you've learned is also part of it. May God help us. I want to end the live stream now. Thank you so much.